Yeah, it really is. It really is. It's fun. It's fun. I'm excited that you have joined us this morning. I'm just waiting for the stream to actually start because there's always like a 15 to 30-second delay somewhere in there. And we're going to connect to the North Richland Hills Club and get their stream pulled in here in just a minute. They're starting at the bottom of the hour at 8:30. Yes, there we go. Awesome. Okay. Good morning, all. I can actually see myself now in the stream. Thank you for watching from YouTube, the Facebook group, and Twitch. Be streaming to all places this morning. And we'll go for probably 4 hours this morning, take a lunch break, and go for 3 to 4 hours this afternoon. It's supposed to go from 8:30 to 5:30 with a lunch break in the middle. Last week, they had about an hour and a half, 2-hour lunch break in the middle, and it ended around 4:30, so it ended a little bit early. We'll see what happens today. I don't know. The stream will keep going until the session ends. So I just want to make sure I got all my ducks in a row here. That's good. Close that. Yes. Okay, good. Discord. Let me know. Good morning to Buiz. I don't know how to say that name. Buiz. I'll take my journal exam next year. I keep getting consistent 90% on my reviews. Haha. Why would you wait till next year? Go take it now, man. Good morning, Kenneth. Good morning, T. Senior, Nashville. Thanks for joining us this morning. You guys let me know how my audio is this morning. Please. Please let me know how my audio is this morning. Okay, I've got to look up this and find the right. I'm going to connect over here, join. Get this meeting started. Their meetings they're probably in the waiting room or something. So yeah, there we go there. Okay, I'm in the waiting room for the Zoom session. We'll go down here. All right, Chester, good morning. Thanks for being here this morning. Terry from Addison, thanks for being here. Ooh, that was quick. Join with computer audio. Mute myself. This camera. Good, okay. So I've got their Zoom. No, that's the wrong camera. I've got their Zoom session up. There we go. On my other screen over here. And we're just kind of waiting for them to get rolling. Let's hide that. Okay, so a couple things this morning. Good morning to Michael, Adam, JL. Thanks for being here.
Morning, Jason.
Ooh, that's loud. Hey, good morning.
You're muted.
Yeah, I'm muted.
Well, I guess there we go. I got my side muted too.
Oh, that's loud. Okay, so their audio will come in a second. Okay, so let's see. Okay, Kenneth, you passed your general last month. Okay, good. Good. And Michael, I'm trying to get my general. Good morning, Roger. Thanks for being here this morning. August. Yeah, okay, good. Well, congrats on passing your general either way, man. T Senior, I have a license question. Where can I send it? You can send it here in this chat. However, you can join the Zoom session that they're allowing people to join, or you can send it here in this chat, however you want to do. So let's see. Okay, so they're going to get started here. Okay, so I show 8:20. They're supposed to start at the bottom of an hour in about 10 minutes. So I'll probably pull their feed over here in about 5 minutes or something like that. Hey, Samer, good morning. Thanks for being here this morning. I will say that tomorrow evening at 7 p.m. Texas time, which is Central Daylight Time right now, On this channel again, we'll be doing another live stream. I'll be welcoming Christian K0STH from 100 Watts on a Wire podcast. It's a very popular audio podcast. It's been out for a long time. Hopefully you guys listen to that. If you are interested, you can join us. He's streaming on YouTube now as well. He's got a new YouTube channel that he just started doing video podcasting on. So he's kind of intertwining it with his audio. He's not quitting audio, but he's kind of intertwining it. He'll be coming on and talking to us about his efforts and about an HF event that he's running next weekend that he calls Fallout. Also, we'll be celebrating the breaking of 50,000 subscribers on this channel, which happened 2 nights ago, about 36 hours ago, something like that. So I'm really excited to see everybody on the live stream tour all evening. So hope you can make it during that time. All right. That stream is already on this channel in a pre-planned state. So the URL is up there, so you can bookmark the URL and come back to it, set a notification, however you want to do that. So anyway, we got about 25 watching now this morning. Once again, we're going to be streaming the third part of the general class from the North Richland Hills Amateur Radio Club. It will start here in about 8 minutes when they just spun up their Zoom session. I'll be bringing their feed over here in just a second. Okay, as much as I want to take the exam now, I can't. The earliest I can is May next year, but then I might get... Okay. Good, Stan. Awesome. Good luck to on your test tomorrow. Buiz, I don't know if I'm saying your name right, but whenever you can take it, man, good luck to you. So, I know that an amateur can hold only 1 grant at a time. Is that just for 3 levels of amateur license? What if I have my professional radio telephone license? The professional radio license has nothing to do with the amateur license. You can have both at the same time. So you can be an amateur general, amateur extra, and have a GROL, GROL. You can have a GMRS license, which is not commercial, but you can have a professional license and an amateur license and GMRS license and multiple other licenses all at the same time. They will follow your FRN number on the FCC ULS, and the only thing they do is they give you more privileges on more different frequencies, on a wider range of frequencies. So amateur license gives you privileges on amateur frequencies. Professional license gives you privileges on professional frequencies, and so on and so forth. So they don't interfere or contradict one another at all. Thanks, Roger. Thanks for being here this morning. Let's see. Chester's in the chat. Or in the Zoom, rather. Okay. Yep. There we go. Okay. All right, I'll show 825, so I'm going to go ahead and bring their audio over, make sure everything's good there.
Covering session 1, which covers chapters 1 through 4. If you want to do sessions 2 and 3, that would be fine. Session 2 covers chapter 5 through 9. And he asked me on session 2.
Okay. Yeah.
I believe that's right.
Yeah, let me double check. I want to see if he's around.
He's playing golf, but you can ask him. He'll answer because he answers.
Yeah, because we want to make sure we get everything covered, and I'm not sure what Tim is covering this after. I know he's covering the last one.
That's session 3, I guess.
Session 4. There's 4 sessions.
Well, I might need to adjust that.
Well, that's...
Because at one time he told me you were doing session 3, and then he said, I'll do session 3 if nobody will, and then...
I'm trying to look for his last one. It's not all cohesive in one place. There's not one final synopsis here. General class. Okay, general class. Week 1.
That's better.
Week 1 is Jeff.
Right.
9:29.
Thank you, Michael.
Jeff has session 1 in the morning, and myself and John
DX I made is
have session
40,
2 in the afternoon.
40 FT8 was
Week
Brazil.
2, Tom
that's
has
fun.
session 3 in the morning, and and Tim has session 4 in the afternoon.
Right. That's what I'm seeing here, but it doesn't tell me what the chapters are, but it would have to be.
Well, it goes back into a previous email where I read to you what he had said.
They're getting their agenda lined out. So
Let me see if I can find it.
Here we go. It's an email on 9/5/20. Class is coming up, and he's saying, Jeff, I have Jeff covering session 1, which covers chapters 1 through 4.
Right.
And if I want, he's talking to me, to do sessions 2 and 3, that would be fine. And then he breaks it down. Session 2 covers chapters 5 through 9. And session 3 covers chapters 10 through 13. So if I go back up to the last one he sent, which was on 9/29, he's going to propose a practice session.
Right.
Wait a minute, that's not the right one. It's another one.
Well, Tom, what I'm seeing here is me on last week. This is a reminder. I have the morning. He and John have the afternoon. You have session 3 this morning, which would be 10 through whatever you said.
Exactly.
And so Tim would have the rest of them this afternoon. So whatever session 3 is, I think is what you'll need to cover this morning.
Okay, I got you. Session 3 is, I see that's unfortunate. I have to go back and see. Session 3 covers 10 through 13. Well,
yeah. So that's what you'll need to cover this morning.
Yeah, that's easy for me to do. I'm just going to.
Hey, Lowell, good morning.
Get out of this now. Can you still see me okay?
Lowell's not on this morning, Jason.
Oh, who's that, Jeff?
Old weird guys.
Okay.
And I'm not going to be on long. I'm just turning it over to Tom here in a minute.
Okay, good. Yeah, I can't. You don't have your video on. I can't see you.
Yeah, I don't have my hair combed. I look like a weirdo this morning. So
okay, all right, no worries.
Don't want that to get out.
We're ready to go whenever you guys are. So just let me know.
Okay.
Yeah. 10 through 14, Jeff, right?
Yeah, whatever he said that session 3 was. If you'll cover that, that'd be great.
Okay, I'm going to send an email to myself here. Hold on a second.
Okay. So for you guys that are already on, Jay, Jared, Chester, I think that's only 3 students on right now. If you're interested in taking the test this coming Tuesday, please let Lowell know. We have some people already scheduled. I think we have 5 slots open, but if we have more than 5 more people that want to join, we'll find some more VEs.
I'm all set.
Have you already let him know you're doing, Chester?
Yep, and I already paid. I'm all ready to go.
Good.
Yeah, this is Jay. I plan on doing it. I need to get that sent today, so I'll get that taken care of.
Yeah, his email is w5hp@att.net. Let him know. And like I said, if we run into more than we have open rooms right now, we'll still figure it out. We'll get some more VEs, or we may have to put you in a waiting queue. And we're going to try to do at least 3 or 4 people at a time if we have enough VEs. So we'll roll through it. Good morning, Ken and Ann Baum.
We're here, the thing connected to the TV, so you may not be able to hear us very good.
We can hear you a little bit. So I don't know if you caught what I was saying. If you're planning on taking the test this Tuesday, please let Lowell know.
Yeah, we're registered and paid.
Good, good. Okay. And so this also, well, he's not streaming yet. I'll let him get it streaming, and then I'll make the announcement and turn it over to Tom in a minute. As soon as Tom tells me he's ready.
Almost.
That's what happens when you use two computers, Tom. Everything's never synced.
Yeah, and see, I've got a laptop, and all of the stuff was sent in
Okay.
through the iPad stuff that
Okay.
was in PowerPoint. Hold on a second. Now I've got to make sure I.
So Jason, we just want to let you know again, we do appreciate you doing this for us.
Absolutely, yeah. Had people commenting on both of the videos from last Saturday. A lot of good feedback. A lot of people that had used the replays to study up and have scheduled their tests and have tests upcoming. So so we're moving right along. It's a good show.
Yeah. I don't know if you heard, I had a guy from Arizona contact me and a guy from Massachusetts yesterday. And he said he watched the replay twice and he ordered his book. It should be here today. And he's getting ready to take his general.
Good.
So seems like we're reaching out. I noticed there were people from all over in the comments. So
yeah.
I went back and kind of scrolled through the comments a little bit. I didn't realize I was going to have to watch the whole video to get all the comments. So I didn't watch it all.
Yeah. Well, you can kind of, the comments kind of follow the theme of they follow the timeline of the videos, but you can fast forward and rewind and, kind of catch it from there. So,
yeah. So are you ready, Tom?
I'm trying to get it into
Okay.
my computer here, so just bear with me.
No problem. Take your time. No rush.
Yeah, look, Jason, I looked at all the thumbs up and stuff. We had like 140 or so thumbs up and only a couple of thumbs down. I'd be interested in what the thumbs down were about. I mean, even though we're like 3, but still.
The thumbs down are because once you get to a certain size on YouTube, you always get thumbs down.
Oh, really?
It doesn't have anything to do with you guys. It has to do it's because it's on my channel. Yeah.
Okay.
Yeah. All the YouTuber guys, we're always talking about that amongst ourselves. Yeah, it's just something that's just the internet.
Okay, because I was kind of, because when you're presenting stuff, if somebody gives you a thumbs down, you want to know what you could do better. So
right.
So I'm just kind of curious what those 3 were. But if you're saying it's just because it was so many people, then I'll go with it.
Yeah.
You have a lot more followers than I do.
Yeah, it's just one of those things you have to deal with. It's not a problem. 97% thumbs up is pretty good.
Yeah. All right, here comes another. Hey, Tom.
And that was 10 through 14, right?
Yes.
Okay, I got them all loaded on my laptop. I mean, yeah. And I'm ready to roll here. So
your audio has dropped down quite a bit.
My audio?
Yeah, it's kind of muffled.
Oh, maybe I've got.
Good morning. I'm not sure if it's Jaime or Jamie, but good morning. Glad you're joining us.
Morning. Thank you. Glad to be here.
For those of you that may not have been last week, you'll remember me. My name is Jeff Grantham. My call sign is KB5WCK. I am the president of the North Richland Hills Amateur Radio Club, and we are glad to have y'all join us. And like I said last week, if you have questions or even some comments on how we can do this better, you can email me at my call sign, KB5WCK @ARRL.net. And for some of those that are your late joining, we did have some people from outside the state of Texas join us. We had a guy from Arizona and a guy from Massachusetts contact me this week about our class. They're watching it over YouTube. For those of you, well, you're not streaming yet. I keep saying for those of you watching on YouTube, but you're not going yet.
Yeah, it's going.
You start whenever you want to.
It's going.
Oh, okay.
It's going.
Good,
yeah.
Good.
Yeah, I started about 8:15, but I didn't bring you guys on until 8:25. So yeah, we're good to go as soon as you guys are.
Okay, well we can go if we're streaming. I'll go ahead and talk to everybody on the internet first, and then we'll turn it over to Tom.
Okay.
I'll make sure I put audio though.
It's still muffled.
It's not real bad, Tom. We can hear you, but it's not clear like it was earlier.
Maybe a few minutes ago it was okay.
It was better a while ago. It's not real great right now, but I mean, you can hear yourself.
Yeah, because I'm not sure where the audio is coming from. It may be that it's picking it up on my, huh?
Whatever you just turned to is what's giving the audio, because it got real clear.
Yeah, that's my laptop.
Well, you may have to switch your laptop.
I'm going to switch it to the desktop microphone. Let's see if that will.
Okay.
While you're
now
doing that,
That's good.
yeah,
is that
that's better.
Much better. So let me finish up here, Tom, and then I'll turn it over to you. So for those of you in the class and those of you on YouTube, welcome. This is the second weekend of the North Richmond Hills Amateur Radio Club General Class. We will be giving a test Tuesday night. We have 5 slots open as of right now for the test Tuesday night. So if you have not signed up and you're interested, please contact Lowell Martin. He's our education coordinator at w5hp@att.net. And if we have more than 5 sign up, we'll round up some more VEs, or we'll just put a waiting room and just roll through them. And you may have to wait a little bit while others take their test, but we'll get you tested. For those of you outside the state of Texas, welcome. We're glad to have you. Tom Phillips, our vice president, will be presenting this morning. And then I forgot Tim's last name. Another gentleman, Tim, will be presenting this afternoon. We will get you through the rest of the general class information. I'm fixing to turn it over to Tom. Oh, real quick. A big thanks to Jason, KC5HWB from Ham Radio 2.0 YouTube channel for live streaming this for us. And so it's kind of like a simulcast. We're doing Zoom and YouTube. Please feel free to comment. Jason's monitoring the comment cube. And if you have anything we can do better, let us know, because we always want to make sure that all the hams that we educate are ready to go and well and have a good knowledge. So with that, I'm going to make Tom the host. Tom Phillips is his name. His call sign is AB5ZJ. And Tom, you are now the host. Take it away.
Okay, I can share my screen right now.
Yes, you should be able to.
Mm-hmm.
Yeah.
Oh.
How's that? Now let's see. Let me get out of this.
We can read your emails other than that.
Yeah.
Yep.
And I'm going to pull up the PowerPoint presentation for the first session here. What I want to do, and I don't use PowerPoint too much, but I want to be able to start it, on one screen and just click from one screen to the next, so I don't have to go down through this. Help me out. Which one do I push? Well, that's good enough there, I guess. Here we go. This is going to be a session on HF transmitters.
We are still seeing your email, so you know.
Yeah, it's still showing your email, Tom.
Is it really?
Mm-hmm.
According to this,
if you have dual monitors, you want to share the monitor with the presentation.
No, I don't have dual monitors. I don't have dual monitors. Let's see what's going on here. There is the one I want. Do you see that one?
There it is.
We can see that one.
That's the right one.
Mm-hmm.
Okay. So this is the HF transmitter then. And let's see, we go down to make sure I've got the right one here. There we go. So element 3, passing the test, your new general bands. Oops, boy, this is why I wanted to get a here, I'll just have to go down. And so see FCC rules, voice operation, CW lives, digital operation in an emergency, and Skywave excitement. And then we go to your HF transmitter, your receiver, This is element 3. I'm sorry, did I mess you up? Oh, sub-element 3. Okay. Element 3, your HF transmitter, your receiver will be covering oscillators and components, electrical principles, circuits, good grounds, HF antennas, coax cables, and RF and electrical safety. Have you seen any of these drawings before in your studies? Anybody?
I have seen a couple.
Mm-hmm. Okay. We'll get into the testing here. In the amplitude modulation area, you will notice that in this, can you see my mouse okay?
Yes,
Yeah, I
sir.
can see it.
Okay. And so this is depicting a sine wave that has even tops and bottoms. You know, the center line is a dotted line, and it has an even plus and an even minus. So you can tell it's a very even wave. But when you inject an audio signal onto that wave, it does the following. The frequency never changes, but the audio causes an amplitude to change of that particular carrier, and that's depicting a carrier. And then we go into a balance modulator, and the balance modulator, it combines the signals from the carrier oscillator and the speech amplifier in order to send the results through a filtering circuit in a typical sideband phone transmitter. And in a sideband transmitter, we'll get to that. The carrier, when they say upper sideband, the bottom is removed. And so is a carrier. So only the upper sideband of that signal is used. If it's a lower sideband, LSB, then the upper side is removed and you have the lower side. So that means that the carrier really only occupies half the frequency of the signal, and it's modulated by the audio. So that's the difference between AM and single sideband. Think of it as AM being both sides and single sideband being one side or the other. Lower sideband being lower sideband, upper sideband being upper sideband. And then we go to the next one. And this is a filter used to process signals from the balance modulator and send them to the mixer in a single sideband. And the phone transmission that uses the narrowest frequency bandwidth is single sideband. As I mentioned, the reason why it uses a narrow frequency is it's cutting off one side of it. So it only uses less bandwidth than an AM signal would do. And this is a kind of circuitry that you would use. We could spend all day going through the theory, but I'm sure that isn't what the course is about. It's for you to understand that you have such a thing as a balance modulator, which is right here. And there is the signal from the carrier, from the oscillator, is being injected into this and combined with the microphone. You can see in this balance modulator, and the sum of that goes out to a crystal filter. So you got the carrier and you got the microphone signal being injected on that carrier, and it goes out to the crystal IF filter, goes through an IF amplifier, and it goes through a mixer again, which has a second oscillator and an IF amplifier, and another VFO signal is injected here to the power amplifier. And the result of all of this is that we only get one side of the carrier out. The next slide, it looks like a picture. It's a speech processor. And the speech processor is showing here increases the average power of a transmitted signal. And the speech processor works on the audio level so that you, I'll see, describe it. If you look at it, if you listen to a commercial on television and you always wonder why the commercial sounds louder than the, they're putting speech processing onto that commercial, and they're increasing the relative audio sound for your ears to hear it better. They want you to hear that commercial much better. And a speech processor does similar things. And the transmitter audio or microphone gain control is typically adjusted for proper automatic level control, ALC. And you'll see that on a lot of transmitters, most all of them. ALC, automatic level control, and you set that so that you don't overdrive the transmitter. Okay, let's move on up here. If a transceiver's automatic level control system is not set properly when transmitting AFSK signals, audio frequency keying signals, with the radio using single sideband mode, improper action of the automatic level control distorts the signal and can cause spurious emissions. So that'll be in the test, I'm sure. The question may be that something to do with the ALC is set improperly, you get a better signal, or they may give you 10, it's a multiple choice question, but please be advised that if it's not set properly, when transmitting an audio frequency keying signal, the keying signal with the radio using us in a sideband mode, then improper action of the ALC distorts the signal and can cause spurious emissions. And the purpose of using an automatic level control with an RF power amplifier is to reduce the distortion due to excessive drive. Remember, automatic level control, think of it as an automatic control. You set it at a certain level that makes the system, the transceiver, see a good clean audio without clipping the signal or causing distortion. And you want to set it at the proper level to do that. And they're telling you another effect of overmodulation is excessive bandwidth. Excessive bandwidth means that if you're overmodulating, you're spreading your signal out in that area of the band that you're talking, and it's causing spurious modulations at the outset of the outer ends of the signal that you're transmitting, and that's definitely a result of overmodulation. I'm sorry about that. And of course, the other thing that will happen is if you got excessive drive, you can do some permanent damage to the power amplifier because of all the spurious and overmodulated signals going into the power amp. You could destroy it. Now, a good modern power amp will have safeguards for that. So you'll want to check your specs. If you're going to buy a cheap power amp, it may not have that capability. And therefore, you've got to be very, very careful to make sure the automatic level control on the transceiver is set properly. An incorrectly adjusted speech processor can cause disordered speech, splatter, and excessive background pickup. So if you have a automatic level control set correctly, you won't have that problem, and your background noise that's in your ham shack won't be heard as much. You definitely don't want a lot of background noise. People talking maybe in the background. If your processor is set incorrectly, you will pick up a lot of that noise talking, which will be loud, and you definitely don't want that. Flat topping is of a single sideband phone transmission is signal distortion caused by excessive drive, and he's kind of got this. So flat topping would be that you can see here's a good signal. Here's one that's been overdriven, and it flat tops the signal. You can see that obviously something's going to go wrong, and it's going to be your voice. Your voice is not going to be clean. So that's flat topping. It flat tops. It cuts off the top of the signal from here to here in this section. It cuts off that top portion, and the degree of flat topping depends upon the distortion that you've injected with improperly adjusted automatic level control. And listen, if you guys got any questions, just chime in. Feel free. Okay?
You bet.
Yep.
One test that is often run on a single sideband transmitter is a two-tone test. A two-tone test analyzes the linearity of the transmitter, and you can see two tones, they're close together. These two tones, they're audio tones, and they're very close together. And when you put them like this close together, your result is over here with this signal, and the result is a clean-looking sine wave. You notice that the negative and the positive go to zero, and the result is giving you a proper adjustment. But if you're distorting it and you overdrive your audio, this two-tone signal will clip the top part, and you won't get that nice clean sine wave, and this will cause distortion. That's what a distorted audio signal looks like. And that two-tone analyzer gives you a good understanding of what happens. Most people don't have this two-tone test. Most people don't. You just have to make sure that your ALC is properly set. And when you get to playing around with your transmitter, that will become pretty obvious. And for the test, just know what ALC is going to be able to do if it's set improperly, which is to overdrive and distort your signal. The modulation envelope of an AM signal is a waveform created by connecting the peak values of the modulated signal. Well, here you can see both sides of the audio waveform, or the signal is represented here, but it goes down and up depending upon what the audio is doing when it's injected into the carrier. And that's a typical AM signal because it affects both sides of the carrier, the positive side and the negative side. And an oscilloscope is an item of test equipment that contains horizontal and vertical channel amplifiers. And in an oscilloscope, you can look at that kind of signal coming from your transmitter or any other device that represents a signal. You'll even, with an oscilloscope, be able to see what a single sideband signal looks like as well, and a whole bunch of other signals. Does anybody in the group have an oscilloscope by chance? No?
No, sir, but if you're donating one, I'll take it.
You're right.
No, you will not need an oscilloscope, but if you're become an experimenter and you really get into ham radio and you want to build your own equipment, I strongly recommend an oscilloscope. I've got one sitting over here. Do you guys see my face right now?
Nope.
Yeah. Well, I was just when you asked the question.
I mean, can you see my me talking in
Yes.
the corner? Let me do this.
Oh, yeah.
Okay, can you see over there where I'm pointing to my workbench?
Yes, sir.
Yeah, you can see the oscilloscope at the far end. I don't know if it shows up on this camera or not.
Yep, it does. I see it.
Yeah. Okay. So I experiment a lot, and I needed that, so I bought one. And there are people that have them for sale, and you can get them very inexpensively. That one is a huge oscilloscope, but it's quite good. And I paid $200 for it. And brand new, that's an HP oscilloscope. That would be probably, I don't know, close to $10,000 or $11,000. So just saying, you know. All right. And of course, it goes on to say an oscilloscope is an item of test equipment containing horizontal and vertical impulse. And they're trying to describe to you how the oscilloscope is. Now, this, of course, is looking at a tube amplifier, and that particular older one that I have has a tube. The newer ones don't have tubes. They have regular LED screens similar to your TV set, and they don't operate anywhere near like this is. But they show you that nevertheless, just to give you an idea that, you know, you have a vertical signal going into one plate and a horizontal signal going into the other plate, which causes the modulation of the electron beam that comes from the filament of the vacuum tube, which is, this is all it is, a vacuum tube, and the electrons then are driven toward the screen to give you a representation of the signal, whatever that signal is. Okay, and oscilloscope is the best instrument for checking keying waveforms. This looks to me like it could be a newer oscilloscope that battery-powered oscilloscope, and it could be an LED screen. So its mechanism for driving the screen is a little bit different than what you see, but the results could be the same. The results can be the same. And these are the type of waveforms then that you would get. This is a keying waveform of a CW transmitter. See, there is a signal, the burst of signal. Actually, the keyer output would be this. So this would be like a dot, and this would be like a dash. Or it could be just a dot and no carrier, and then another dot. So that's what the carrier would end up looking like if it's a CW signal. A CW signal, by the way, it just interrupts the carrier. So you always have a very clean sine wave, and you're just interrupting the carrier with the tone, the CW tone that you inject into the carrier. And this is depicting an attenuated RF output of the transmitter. It's a signal source that is connected to the vertical input of the oscilloscope when checking the RF envelope pattern of a transmitter. We talked about that. Again, they're talking about one advantage of an oscilloscope versus a digital voltmeter is that complex waveforms can be measured. A digital voltmeter is a digital voltmeter. It'll measure things in using numbers. But a waveform like this is very telling, and it will show exactly what the signal looks like. And if you reference it to a straight line across the scope, like this, then, and you adjust it, you can adjust it with your little knobs to be even. This is, let's say this one is the same here. So now you can tell that this is 1 volt and this is 1 volt or something like that. I'm using that as an example. And it goes downward. So you can take a look and see right there at that level, at that spot, what the signal is in the positive and what the signal is in the negative until it peters out. It just goes down. That's a damped oscillation. So that means when you click on a key or something like that, it may oscillate for a while and then just dampen down to nothing. It goes down to nothing. And that's exactly what the signal would look like. Boing. And then, you've heard of a tuning fork when it you click it and it starts out loud and then eventually decays. And that's what the waveform would actually look like if you were to measure it on an oscilloscope. Time delay, sometimes included in a transmitter keying circuit, is used to allow time for the transmitter / receiver changeover operation to be completed properly before RF output is allowed. The reason for neutralizing the final amplifier stage of a transmitter is to eliminate self-oscillation. And really and truly, in a keying circuit, if your keying circuit is clean in the beginning of the transmitter, it will then reach the oscillator, and the oscillator, the final amplifier, will amplify this cleanly so that it will not have any overshoots. And they're trying to show you here in this yellow part, there is an overshoot. That meaning that the RF amplifier itself may be starting to oscillate itself. And that's why they call it self-oscillation, where the RF amplifier is an amplifier, but if improperly, if a signal is improperly input to it, it can break up into its own oscillation, which you definitely don't want. This would be the cleaner signal down here, the way it looks in this blue line. Can you guys see that okay? Is my screen big enough?
Yep, I can see it.
Yeah. So in this frame here, the key takeaway is to understand that a time delay is sometimes included in a transmitter keying circuit to allow time for the transmit receive changeover. Transmit receive, and the transmit receive changeover operation to complete properly before the RF output is allowed. So just be advised that if it is not properly done, if the time delay is not properly done, then you get this additional ringing that goes on inside the power amplifier, which results in distortion of the signal and changes the way the signal looks in the RF envelope. And anything other than a nice clean signal like this blue line, as represented by the yellow up here, will cause distortion in the actual carrier itself. And keep in mind that the reason for neutralizing the final amplifier stage is to eliminate self-oscillation. I don't know if that's going to be in your test exactly that way, but they'll give you something that'll say something about eliminating self-oscillations and keep that in mind. All right, let's see. Frequency modulation is the name of the process which changes the frequency of an RF wave to convey information. Now we're going to get into FM, frequency modulation. FM would be your radio station that you listen to on 101.1 or 96.8, in the FM broadcast band. FM does not change the amplitude of the carrier. It actually changes the frequency of the carrier. So, for example, if the frequency of the carrier was, well, let's make it simple, 1,000 hertz, and you FM modulated that 1,000 hertz with a 10 hertz carrier, you would actually stretch out the signal like it shows here. Here is a straight carrier. Here's the signal that is being injected, and here would be the result, where you see that the frequency itself is shifting, as it is right here. Carrier frequency modulated. You see the frequency starts out okay, and then it bunches up, and then it changes. That definitely is being modulated, but the frequency itself of the signal is being modulated, and the receiver has a means in the FM receiver to be able to pick that up and separate the carrier and take out only the audio for listening. So frequency modulation changes the carrier frequency. AM modulation does not change the carrier, it changes the amplitude. And again, repeating single sideband eliminates one side of the carrier or the other and injects its audio into the upper sideband or the lower sideband. FM actually changes the frequency of the carrier, and that change in frequency can be detected, and with the proper electronics be analyzed, and the audio itself will be the result. Eliminate the carrier and keep the audio. The multiplier, they're talking about a multiplier is the name of the stage in a VHF FM transmitter that generates a harmonic of a lower frequency signal to reach the desired operating frequency. That's a lot of theory there going on. In a VHF FM transmitter, like a handheld transmitter for 2 meters and 440, that type of transmitter, which is FM modulated, what they do with a multiplier is it generates a harmonic of a lower frequency signal to reach the desired operating frequency. A harmonic is a sub frequency or an upper frequency. I'm trying to see if I can do this. For example, if you had 1,000 hertz, a subharmonic of that might be 500 hertz using a multiplier, or it might be 1,500 hertz. So by using that multiplier, we can then create a harmonic of that. And by the way, all audio frequencies have some kind of harmonic. There's some degree of distortion in just about any signal. It may be so low you can't measure it adequately without a proper instrument like an oscilloscope. But certainly a piano, when it comes to mind, when you play the key of C or whatever, there are harmonics that can be generated from the key of C or any other key. So just keep in mind that harmonics are actual upper, how do you say it? Upper levels of a given carrier. So 16 kilohertz is the total bandwidth of an FM phone transmission having a 5 kilohertz deviation and a 3 kilohertz modulation frequency. And it goes on to say total bandwidth is equal to the peak deviation plus the highest modulating frequency times 2. Because the FM signal is symmetrical about the carrier frequency. In this example, the total bandwidth would be 5 kilohertz plus 3 kilohertz times 2, or 8 kilohertz 2, or 6 times 2, or 16 kilohertz. Boy, that's a lot to remember, but the takeaway here is the total bandwidth of an FM phone transmission is 16 kilohertz when you modulate the thing. And you have a 3 kilohertz modulating frequency. In other words, your audio would be 3 kilohertz wide of the frequency that you're using, maybe voice. Then you have a bandwidth of a transmitter, of a phone transmission having a 5 kilohertz deviation, meaning you can inject a 3.5 kilohertz signal into that and be okay. If you go beyond the 5 kilohertz allowed area here that's set by the electronics, you're going to get distortion. But and so they're trying to tell you here is that the key takeaway on this one is 16 kilohertz is a total bandwidth of an FM phone transmission signal that has a 5 kilohertz deviation and a 3 kilohertz modulating frequency. And then they give you the example down here. In this example, the total bandwidth would be 5 kilohertz. That's the bandwidth of the deviation. And plus injecting a 3 kilohertz modulating frequency into it times 2, giving you a total of 8 kilohertz times 2, or 16 kilohertz would be the total bandwidth of this signal. The way this would work out. If this was 6 kilohertz and this was 4 kilohertz, you'd put it in here. But I don't know how they're going to answer that question or ask that question, but keep in mind that the summation of the frequency of the transmission having a 5 kilohertz deviation and a 3 kilohertz modulation, that's 5 plus 3. So they're going to probably ask you, and they'll give you a multiple choice that would end up with this answer or some other answer. But you've got to be sure that you understand that this plus this times 2 equals 8 times 2 equals 16. A lot to remember, but that's what studying is all about, I'm sure. Here's an HF transmitter of 416.7 hertz is a frequency deviation of a 12.21 megahertz reactance modulated oscillator in a 5 kilohertz deviation. 146.52 megahertz is the phone transmitter. So this would be the ham band up here, 146, and this is the frequency deviation that they're talking about here in this example for a 12.21 megahertz reactance modulated oscillator. And now you're getting into the weeds here. I don't know how they're going to come up with a question on that, but it seems that the takeaway is that since the FM deviation is also multiplied, there will be much less than 5 kilohertz deviation on the oscillator that is being multiplied up to the transmit frequency. So the multiplier would be 146 divided by 12.1 megahertz, or 12. Therefore, if we desired a 5 kilohertz deviation at 146.2 megahertz, 52 megahertz, would only need 1/12 of that at 12.21, or the required deviation would be 5 kilohertz. 5 kilohertz. divided by 12, or 416.66 hertz. That's a lot to absorb, by the way, but I don't know what to give you other than in this particular case, you're going to have to really study that and understand what deviation is in terms of, the deviation and how the deviation affects the frequency. And that's in the math here. So they'll probably ask you a multiple choice question, and there will be something in there that will talk about the deviation. Here they're showing a 2-meter rig in a school gym ready to make contact with the ham station. That's a 2-meter rig. The frequency they're talking about up here is in the 2-meter ham bands. Now we'll get into another deal. Phase modulation is produced by a reactance modulator connected to a power amplifier. Phase modulation is the name of the process that changes the phase angle of an RF wave to convey information. Let me see. There we go. To determine the efficiency of an RF power amplifier, divide the RF output power by the DC input power. Example, a 100-watt 2-meter power amplifier that draws 10 amps from a 13.8 volt power supply has an efficiency of 72%. Efficiency equals 100 watts or power divided by the voltage times a 10. And the efficiency is 100 divided by 138, or 72%. They're going to ask you about the efficiency, definitely. To talk about phase modulation, I would have to show you, I'm hoping they would show you another signal. It might be coming up, because you can't show what the phase modulation is without a waveform in front of you to look at. And let's see if this other one comes up here. No, it isn't showing you what the phase is. Trying to, if a sine wave is straight up and down vertically on your screen, and you look at a sine wave like this here, and you want to know what the phase of it is, imagine this peak signal and this peak signal shifting slightly at a 45-degree angle. And that would represent the phase of that signal. A phase would be viewed as a circle from 0 to 360 degrees. So if I shifted this thing 45 degrees off its axis, like I'm showing you here, that would be 45 degrees. It'd be a 45-degree phase angle of that signal. And literally, transmitter electronics can adjust the phase or modulate the phase of that signal rather than the actual carrier of the signal or the frequency of the signal. And it has another area which it can modulate, which is the phase. Consider that signal, therefore, in your mind as being tilted 45 degrees from dead center in a simple circle, 360-degree circle. I hope that helps out there. And then the output PEP of a transmitter is 100 watts. If an oscilloscope measures 200 volts peak to peak, 200 volts peak to peak, across a 50 ohm dummy load connected to the transmitter output, then you have a formula. PEP is a 200 volts divided by 2 times 0.707, you got to remember that, squared, 0.707 squared times divided by R. And then PEP is 70.7 squared divided by 50. And that comes out to 4,998 divided by 50, or PEP, peak envelope power. PEP is called peak envelope power. Peak envelope, that's an envelope, would be 99.97 watts, close enough to 100. And 625 watts is the output peak envelope power from a transmitter if an oscilloscope measures 500 volts peak to peak, 500 volts peak to peak, across a 50 ohm resistor connected to the transmitter output. And indeed, this will be the formula. And in this little chart up here, this is the formula for determining I, power, resistance, or voltage. And these are the components. That's a handy little a chart that you can deal with here. So if you want to find I, you would use this section right here, P over E, the square root of P over R, and then the result would be E over R. And indeed, you would get 624.81 watts. Close enough. And this is something, guys, that I know you're going to have to study. And how they give it on the test will be probably, again, multiple choice question. But if you can figure out the math on this and remember what it does, you should be able to choose the right answer on this one. But it does require some study on this. Again, I know I'm going through these things, but I'm hoping you're taking a look at them and realizing that study on this test is extremely important. And of course, I can spend all day on the theory of this, but it wouldn't do you any good, because then I wouldn't be able to get through all the other questions that we have. The ratio of peak envelope power to average power for an unmodulated carrier is 1. Unmodulated, you just have a sine wave. An unmodulated carrier is a simultaneous peak and average. So 1,060 watts is the output peak envelope power of an unmodulated carrier if an average reading watt meter is connected to the transmitter output indicates 1,060 watts. A steady carrier illustrates both a peak power as well as the average power. Oops. And oh, wow. A 2 times increase or decrease in power results in a change of approximately 3 dB. And boy, you got to study decibels. We have no time at all to go through and understand decibels, but decibels is a log of that particular signal that you're talking about, an audio signal. And decibels can be used in RF as well as audio. A signal, so let's say I increase the sound level. We'll deal with sound rather than RFs because you can hear it in your ear and understand this. If you increase the sound level twice, the change, what they're saying is, in other words, you're increasing the power of the sound. So I've got a soft C, I'm pressing on a keyboard of a piano, very soft, imagine that in your mind. And then the next time I bang on it. And obviously the sound is going to increase in level. Well, they can measure this in terms of decibels. So a 2 times increase or decrease in power results in a change of approximately 3 dB. And the way that they measure this is by using the dB scale. They give you a scale here in signal strength, and they give you over here the math involved in understanding what a dB is. And so just keep in mind about this general idea of a 2-time increase in power results in a change of approximately 3 dB. They might even ask you that particular question. They may ask it in a way as it's going to be 2 dB, 1 dB, or whatever. But this is something to look at. It's something that it gives you an idea of how all of the power from RF and audio is measured in decibels. Any questions on that? Are you okay so far, you guys?
I'm doing good.
How many are still on this thing? I'm not looking at any of the.
I'm still here and we're still doing great.
Okay. All right. Now we'll talk about S meter readings, signal strength. Again, you'll notice in the little chart, what's this here? Tom has entered the meeting room for me. Okay, I will admit him. Welcome aboard, who just entered. I admitted him. I'm screen sharing. Okay, that's cool. So you see in just about any RF transmitter, whether it be a handheld or whether it be a HF station, you will see the S meter. The S meter on a distant receiver they're talking about, from an S8 to an S receive. Let's see, to make an S meter on a distant receiver rise from an S8 to an S9, okay, you would have to raise the power output of your transmitter approximately 4 times. Again, this goes back to the dB. And in case you want to see an S meter and stuff like this, this could be a good time for me to bring on my radio here. Now, I'm going to show you what this looks like. Can you all see that? Can you all see my screen that I'm showing?
Yes, sir, we can.
Yep.
Okay, I'm going to move in a little bit. Tell me if it starts to get distorted, out of focus.
Looking good so far.
Huh?
Looking good so far.
Still looking good?
Yes,
okay.
Sir.
All right.
A little glare.
A little glare? Oh, let's see if I can turn down the glare here.
Well, that looks good.
A little better?
Oh, yeah.
That's perfect.
Wait a minute now. Hold on. I'm going to get a little pointer so I can point to what I'm trying to say here. This radio, by the way, is a ICOM 7300, and it has a waterfall display on it. But now, you notice right here, there's a little signal moving back and forth, and there's a letter S right there. That's a signal strength that you will see, and it has scales on it. S1, S3, S5, S7, S9, and then it goes into a red area here, if you can see that, plus 10, plus 20, plus 30. That's like saying when it reaches S9, that's a very good signal. And if you go over that, that's 10 over S9. It could be 20 over S9, or it could be 5 over S9. So that scale represents what they're talking about in the test. So that you have an S meter reading of 0 dB, there's nothing there, or it'd just be noise. You could hear it way in the background. In fact, what I'll do, is I will remove the antenna, and you'll notice now there is no signal. And you can hear it. I don't know if you can hear my signal. Can you hear the noise that it makes right now?
Yep.
It is coming through, all right? So when I switch it over to the waterfall, the actual signal, that's what's going on in the waterfall display. Now, when we come to a carrier, go to somebody strong. So look at his carrier. There's some up and down movement. So you can see as he's talking, that signal strength goes up because this is single sideband, and we're modulating one side of the carrier or the other. And the result of the thing is the signal increases or decreases. If he's talking normally now, he's up to S9. Can you all see that?
Yep.
Okay. All right. I just wanted to show you that so you could make sense of what we're going to talk about next here. So in that situation, he was coming in. To an S9 on the carrier right here, S9, and maybe every once in a while he might get a little bit beyond S9. Now, if he's running 100 watts and he is an S3 signal, let's say, what this is saying is in order to increase the signal on that receiver that I showed you, one S unit, which is between here and here, that's S3, that's S4. Can you see that? What my pointer is pointing to? So
yes,
this is one. Yeah, this is one dB between here and here. To increase the signal 1 dB, if I'm running 100 watts, and that's the best I can do at 3 dB, but I have an amplifier that I can switch on and talk, and the transceiver connects to it. And now I'm talking and it has 400 watts instead of 100. I will move that needle approximately 1 dB. So what they're saying is changing the signal from S8 to S9. Now, in my example, I use S3 to S4, but it could be S8 to S9. It doesn't matter. It's 1 dB difference in that scale. That represents 1 decibel difference. To do 1 decibel difference, to increase my hearing capacity of 1 decibel on that receiver, I've got to go to 4 times the power. I mean, that's an incredible thing to get in your mind. And when we talk about signal strength, we can talk about signal strength in making it increase in power of 1 dB in other ways besides increasing the power of the transmitter. So for example, I have an antenna out here on my QTH, my location, where it's a long wire and it's transmitting signals in all directions, up and down. But if I was to have a more efficient antenna, let's say if it's a quarter wave antenna, meaning it's very short, and I make it longer and increase the wavelength of that antenna, there is a good chance that I can increase the relative power that's being received by the receiver. So if I can increase my signal by making a more efficient antenna, then in effect, if I've gone from an S3 to an S4, I've effectively, by just changing the efficiency of my antenna, I've increased my power at the receiver, my relative power. So it isn't only by increasing the power of the transmitter itself to consider, it is also increasing the efficiency of the antenna. And you know, a lot of ham operators have beams where they become like flashlights, and they'll come across, they'll rotate around and focus on your location, and a lot of the signal will go to your receiver from their transmitter, and that the amount of signal that is sent to you is determined by the gain of the antenna and the propagation conditions at the time. But if that gain of the antenna is 12 times the gain of the actual signal at 100 watts, that's an enormous increase. So if I have a gain of 12, that means that I'm going to have a change of almost 2.5 dB gain that will appear in your receiver. Your meter will show up 2.5 dB higher. That's a large increase. And the reason why I did that, 12 dB gain, 12 dB gain is a gain of 12 dB. If you take 4 and you divide it into 12, I'm sorry, that'd be 3 dB gain. That would be a 3 dB gain from 3 to 5.5. That's how big a signal change just by using a more efficient antenna like a beam antenna. So gain, dB gain on a signal strength meter can be due to power, increasing the power 4 times the power, or by increasing the efficiency of your antenna. I delve on that a lot because there's an awful lot of things going on here, and certainly S-meter readings are a big thing. So assuming a properly calibrated S-meter, an S-meter reading of 20 dB over an S9 is a 100 times stronger compared to an S9 signal. So 20 dB is 100 times stronger, and indeed it is. So here is a scale that you can look at. 0 dB, 5 dB is 2 times, 6 dB is 4 times. All right, enough said with that. Let's then move on to the next thing. They're talking about another type of amplifier in order to modulate the signal. A Class C amplifier is not linear, meaning it's not nice and sinusoidal, nice and, can consider a straight sine wave, a nice carrier. A Class C power stage is approximate for amplifying an FM modulated signal. Appropriate for modulating an FM signal. A Class C amplifier, they have a higher efficiency. Oops, I keep forgetting that. I don't need to do that. So here's the lowest distortion. Here is the highest efficiency using this kind of a chart. This chart is similar to an HFE chart in a transceiver. And these are the steps that is a collector to emitter voltage. These are the steps. And the bias point would be right about there, would be in the center. And this would be what you'd get. The signal, I'm sure they'll ask you something like a multiple choice question. A Class C amplifier has the highest efficiency, or it has another multiple choice has a lower efficiency, has a no efficiency, or whatever. So remember, this has Class C amplifiers have the highest efficiency of modulating a signal. Moving on down the next signal, linear amplifiers are usually Class A amplifiers. Low distortion is a characteristic of a Class A amplifier. A linear amplifier is an amplifier in which the output preserves the input waveform. And this is because 100% of the waveform is amplified. They are therefore most appropriate for amplifying phone signals. Okay, the correct adjustment for the load or coupling control of a vacuum tube RF power amplifier is to adjust for maximum power output without exceeding maximum allowable plate current. The plate current is determined by the circuit and how much is the maximum allowable plate current. So you just want to make sure you adjust the RF, adjust the maximum power output that does not exceed the actual plate current. They're talking about plate current here. In today's world too, is also solid state amplifiers. And many of the amplifiers prevent that from happening, that you cannot overdrive the thing. So your questions might come down to talking about the correct adjustment is to adjust maximum power output without exceeding maximum allowable plate current. The question may throw in another variable there and throw you off. So just keep this in mind when trying to answer that. 100% of the power of the 100% of the waveform is amplified using a Class A amplifier. A pronounced dip on the plate current meter of a vacuum tube RF power amplifier indicates correct adjustment of the plate tuning control. A pronounced dip in the plate current. And boy, I tell you, you guys would have to see this and have such a device to see what that means. In the old days when I used to measure this kind of thing, grid current, plate current, is when you adjust the grid current. The grid current is, let's say, the input, how much input you give to the tube. And if it's properly adjusted, it will dip the plate current. A pronounced dip in the plate current meter of a vacuum tube RF power amplifier indicates correct adjustment of the plate tuning control, which is the grid control. When the plate tuning reaches resonance, the plate current will dip. When it reaches resonance, so meaning that you're tuning the plate tuning of the power amplifier, which is looking into the antenna. And if you're tuning the plate tuning capacitors, I hope they show this, there will be a point in when the plate current will show a dip, and that will be at resonance. And it shows a dip at resonance because the matching of the signal, the matching of that signal going into the resonant antenna at that point does not take a lot of power. It will actually show a dip in power to a point where it is resonant, and it doesn't drive it any more than is needed in that case. Oops, let's see here. Okay. The HF transmitter. This is the next. You guys want to take a break, 5-minute break here?
I'll be okay with that. We can keep talking or take a quick break.
Okay. Well, feel free. I mean, just raise your hand and tell me.
Okay.
All right. What type of modulation varies the instantaneous power level of the RF signal? Phase modulation, frequency modulation, spread spectrum modulation, or amplitude modulation? What would you say is the guess on that one?
I do believe it's D.
Amplitude.
What type of modulation varies the instantaneous power level of the RF signal? D. You say D.
I think for the animation to work, you have to be in presenting mode.
Yeah, don't I? In order to get the answer on that?
Correct.
What? Let's see. What do I have to do to get up to presenting mode here? I've got a huge 43-inch screen, and I have to actually stand up to look at what it says. Insert, draw, design, transition, animation, slideshow. That's what I need, huh?
Yes, sir.
The slideshow. The slideshow from the current slide. I'll go from the current slide.
Correct.
Let's see what that does. There. Now, there's I can see you guys in the center of this thing. Does that thing I've got in on the screen, is it overlapping the things that you see?
Right now, I just see the slideshow, so I think you might have to minimize the slide, the clips.
Yeah, I have to minimize the clips, but let me see. Get back. I've got to get those clips minimized, and it doesn't show up when I'm on the main screen here. So I've got to go to. Bear with me for a second here. I've got to find out where the thing exists. Usually, since I'm sharing the screen, it doesn't show up. Let's see. Slideshow from current position. Let's see. So I'm trying to figure out how to get that out of there, and I'll be darned, it sits right in the center of all of that, and I'm unable to. My mouse doesn't move or nothing. Let me go back. So let's see. First, I've got to find out where my thing is. I'm going to have to minimize. Let me do it this way here. Yeah. Hold on a second. Somehow or another, I've got to see that other part of the screen. Okay, there is my stuff. Let's see if I can minimize it here from here. Boy. It doesn't show where I can minimize my screen. And the funny part is I always get to see the video of everybody, and I don't see it now. Maybe what I have to do is stop sharing the screen for a minute and see where if I can get the video and minimize it and then come back into sharing mode. So bear with me, guys. We can take a few minutes break here anyways. There.
No problem.
Now I can see it minimized. Let's see if I can minimize it now. Minimize. Okay. Now, if I minimize it, okay. Are you guys still there?
Yep, I'm here.
Okay. I'm just trying to find out.
Yep. Ditto.
When I minimized, oh, there it is. There it is. Let's see if Jamie's on there. Who's on right now? Jamie?
Sir, I'm here.
Okay. And anyone else? Sing out. Just give me a list of people right now. Call by name. Jamie is one, and who's another one?
Chester.
Chester. Okay. And anyone else?
Jay Patton.
Patton. Jay. Okay, Jay. And I'm sorry. Go ahead.
Ken and Ann Baum are here as well.
Ken and Ann Baum.
Oh, okay.
Hello.
Hello. Hello, guys. So while we're taking a little break here, I'm trying to reach a point where I see all the videos. Exit, minimize video. Let's see if there they are again. Now, the idea is to make sure the video doesn't overlap. I got one chat line here. Somebody said in a chat here, clicking on slideshow on top and start put it. Yeah, I didn't see that. When I'm running, I don't see any of this stuff when I'm using the slideshow thing for PowerPoint, but I got it. I got the chat.
Yeah, Microsoft's not very friendly on showing that information anymore.
Yeah, with the new Edge stuff and everything. Yeah, I hear you. Okay, so now let me see. I'm just trying to find out if I minimize the screen. Well, first of all, I got to share the screen.
Yeah, share your screen. I think I have an idea.
There's the sharing of the screen. Now you guys should see that. Now I can see this and I can minimize it. I think I've got it now. It puts everything back up to the side. And if I minimize everybody, I can get back into the list. Let's see how that works. Okay. Now you guys see this, right? You see this? You see my screen?
I do.
Okay,
yes,
and then I'm going to go and do the slideshow, and I'll do from the current. Let's see if that thing shows up. Aha! I did it. Are you guys still there? Are
I'm
you
still
still
here.
there?
Yes, sir.
Okay. Okay. All right. So phase modulation, frequency modulation, and amplitude modulation. Let's see what the answer was. Amplitude modulation. See if it comes up with the answer. There it is. Amplitude modulation. Okay, now if I hit the space bar again, it should go to the next question. Okay, which circuit is used to combine signals from the carrier oscillator and the speech amplifier, then send the result to the filter in a typical single sideband phone transmitter? A mixer, detector, IF amplifier, or balance modulator?
The only thing I see is the same slide as before.
Yeah, the slide's not moving for us.
It isn't.
No,
Really?
sir.
Do you see the slide now?
Yes.
And let me move it to another. Do you see a change?
Yes.
When you're clicking on it, we just see the main program where you make edits and stuff on, not the slideshow itself.
Try clicking on from current slide up there.
Well, what you should see now is your whole screen filled with this mixer detector thing that we're talking about, and then up at the top you should see a ribbon, right?
Yep, that's what we see is the ribbon.
Okay, now when I change that slideshow and I go into from the current slide, if I click on that, it blanks out and then comes back and shows the screen, which you guys still see, right?
Yes.
Correct.
Yeah. Okay.
I'm supposed to do that. So just continue as you were. I think that'd be the best way to go.
Yeah, but if nobody can see what my next slide is going to be. So for example, this is showing balance modulator. So if I go and click on the space bar, or do I click, if I use the mouse or click on the space bar, it should be the same from what I understand and remember about PowerPoint. But you just use the space bar and it shows balanced modulator. Now, if I click one more time on the space bar, I should move to the next slide. And it does on mine.
But not on the screen share.
But not.
Correct.
Is that a clue? Okay, well.
You've got
now,
the
you
wrong
can see it
screen
now?
shared. You've got
Yes.
the wrong window shared.
Can you see it now? All right. So then we'll trick it out here, and I'll do. This is the when I'll read the thing, and then I'll put it full screen because you can't see it going full screen when I do it this way. So we'll do a little workaround here. Which of the following is used to process signals from the balance modulator and send them to the mixer in a single sideband phone transmitter? A carrier oscillator, filter, IF amplifier, and RF amplifier. Which of the following is used to process signals from the balance modulator and send them to the mixer in a single sideband phone transmitter? Which one do you think?
I'm going to go C.
IF amplifier. Okay. Anybody else?
Yeah, C.
Okay. So now I'm going to switch to that thing, and I'm going to hit the space bar, and it's B, the filter.
Oh man.
Okay, here we are. We're going to go that. We're now going to do the next one, the next slide, and let's see. This one here was this one here. That was the last one we did. That's this one now. Single side. Okay. Which of the following phone emissions uses the narrowest frequency bandwidth? Single sideband, double sideband, phase modulation, and frequency modulation.
A.
Yeah, A.
A, single sideband. All right. So we go from the current view there, and we press the space bar, and it is A. I'm sorry we have to do this, but it gets the work done, right? All right, next question. What is the purpose of a speech processor as used in a modern transceiver? Increase the intelligibility of transmitted phone signals during poor conditions, increase transmitter base response for more natural sounding single sideband signals, prevent distortion of the voice signals, or decrease the high frequency voice output to prevent out of band operations.
That would be A.
Increase the intelligibility of a transmitted phone signal during poor conditions. Anybody else with another idea?
That sounds
I'm
like
listening.
I like A.
Okay. All right. I have in my mind, I have a different answer, but let's see together. You know, I have an extra class, the highest class that you can get, but I took my extra class test in 1994 when you had to also know code. And I went through a lot of things, and I'll tell you, you forget because you don't use them every day. But you still have to take the test. I'm glad you guys are doing it, not me. Okay, so from current position, okay. And it's A. You guys are right. I was wrong. All right, be ready for the next one. Okay, and the next one is, which of the following describes how a speech processor affects a transmitted signal, a transmitted single sideband phone signal? Increase the peak power. It increases the peak power. It increases the average power. It reduces harmonic distortion, or it reduces intermodulation distortion. Which of the following describes how a speech processor affects a transmitted signal, a single sideband signal? What would you say?
B.
Yeah, B.
Increases the average power. Okay. Anybody else want to guess? All right. B. You got it right. Increases the average. Did everybody say B?
I said B.
Okay. All right. What control is typically adjusted for proper automatic level control setting on an amateur single sideband transmitter? The RF clipping level, the transmit audio or microphone gain, antenna inductance and capacitance, attenuator level. What would you say is the answer? What control is typically adjusted for proper automatic level control settings on an amateur single sideband transceiver?
I say B.
The RF clipping level, transmit audio or microphone gain.
Isn't
All
it
right.
Agree. B.
B. Okay. And B is correct. I had that right also. Okay. The next one. What is likely to happen if a transceiver's ALC system, automatic level control system, is not set properly when transmitting AFSK with the radio using single sideband mode? Okay. ALC will invert the modulation of the AFSK mode. Improper action of ALC distorts the signal and can cause spurious emissions. Or when using digital mode, too much ALC activity can cause transmitter to overheat. And all of these choices are correct. What would you say?
All of the above.
Yeah, all the above.
All the above. ALC inverts the modulation of the AFSK. Improper action of the ALC distorts the signal. When using digital modes, too much ALC activity causes transmitter to overheat. So you say all the above. Remember that one? That was that improper action of ALC distorts the signal. Remember that I was talking about if you had higher ALC, it would distort the signal.
So is it B?
Okay. I'm going to try to get up here. Okay. What is a reason to use automatic level control, ALC, with an RF power amplifier to balance the transmitter audio frequency response, to reduce harmonic radiation, to reduce distortion due to excessive drive, to increase overall efficiency? Any guesses?
D.
D.
Say that again.
D.
B. B, to reduce harmonic radiation. What is the reason to use automatic level to control ALC power amplifier? Okay. Excessive drive power. D.
Yep, that's what I said. D is in Delta.
Yeah, right. Wait a minute. Insufficient drive power. Yeah.
It's a different question.
That's a different question. What did I do here? What is distortion leads? Was that the last one?
This is one we were just working on.
Okay, and I switched. It didn't switch to the one I wanted. Something was wrong. Okay, let's say, what is the reason to use automatic level control ALC with power? And what was your answer? to balance the transmitter audio frequency response, to reduce harmonic radiation, to reduce distortion due to excessive drive, and to increase overall efficiency. And your answers were?
C.
B. Anybody else say B? B is in boy?
B is in Bravo.
C.
B is in baby. And one says C. Okay. I hear laughter in the background. C is correct. Remember distortion, ALC. If too much ALC is in, it distorts anything. Yeah. Okay. Now, the next one is, what condition can lead to permanent damage to a solid state RF power amplifier? Insufficient drive power, low input SWR, shorting the input signal to ground, and excessive drive power. And your answer is?
D.
Delta.
D.
Yes. I think we all got that one. Okay. And the next question is, which of the following is an effect? Which of the following is an effect of overmodulation? Insufficient audio, insufficient bandwidth, frequency drift, or excessive bandwidth?
Delta.
Delta.
Anybody else out there?
Delta.
Okay, let's see. Excessive bandwidth, correct. Which of the following can be the result of incorrectly adjusted speech processor? Distorted speech, splatter, excessive background pickup, all of the answers.
This is an
D.
D is in dog?
Delta.
Yes, Delta.
Delta. Okay. And I vote for D also. A, distorted speech. I'll be darned. Is that correct?
Huh.
I thought all of the.
No, I'm pretty sure that's everything.
Yeah.
book
I-
your space bar.
it didn't rotate. Let me go do that again. Let me make sure that picked up the right one. I don't know. I would have rotated it. No, it just changed the way it displayed itself. Distorted speech. I don't buy that either. I think if the speech processor is incorrectly adjusted, you will get excessive background pickup. Remember, I was telling you, a speech processor allows you to do some compression, and a speech processor, even on a standard amplifier that like a PA system, if you increase the speech processing power, you pick up a lot of background noise. And if you overdo it, you can get splatter. And if you really overdo it, you'll distort the speech. So to me, I don't believe just distorting the speech is. I think all the answers are correct on that one. But that's a trick question, so you'll have to remember that one. I'll tell you what, when you review your questions on your own, with your own computer there, make sure that that's correct, because I'm not sure that thing was done correctly. Okay, what is meant by flat topping when referring to a single sideband phone transmission? Signal distortion caused by insufficient collector current. The transmitter's automatic level control is properly adjusted. Signal distortion caused by excessive drive. Or D, the transmitter's carrier is properly suppressed.
C.
Charlie.
G and Charlie.
See, everybody else agree with that out there?
Yes.
All right, I hear the yes. And the answer is C. Okay. Very good. And that's true. We went, remember that flat topping thing, the waveform that we looked at the time. I was glad I was going through it that way. All right, let me get up here. Okay. Linearity. Now, if I select this and I go to the answer here, it should give me the ability to do that. Let's see. Yeah. Now when I do press my button, it will my spacebar, it will give me the right thing. So what type of transmitting performance does a two-tone test analyze? Linearity, percentage of suppression of carrier and undesired sideband for single sideband, percentage of frequency modulation, and percentage of carrier phase shift. Remember the two-tone test? Imagine in your mind those two signals sticking up there close together. I was showing you that and talking about it. So what do you think it would be the answer?
A, linearity.
A.
Anybody else out there?
Okay.
All right. A is the answer. Let's go to the test. What signals are used to conduct a two-tone test? Two audio signals of the same frequency shifted by 90 degrees, two non-harmonically related audio signals, two swept frequency tones, two audio frequency range square wave signals of equal amplitude. A little tricky on the question there, but there's a good answer.
I think this is B.
Yeah, bravo.
Anybody else out there say something else? Okay.
I like C. But
C, two swept frequency tones, all right? Well, the answer is B, two harmonically related audio signals. Remember, those two signals, they were harmonically related. They were close enough together, but they were harmonically related. Okay. Okay. What is the modulation envelope of an AM signal? The waveform created by connecting the peak values of the modulation signal, the carrier frequency that contains the signal, spurious signals that envelope nearby frequencies, or the bandwidth of the modulated signal. The bandwidth of the modulated signal. What is the modulation envelope of an AM signal?
I think alpha.
The waveform created by connecting the peak values of the modulation signal. Okay. Anybody else have a choice? A is correct. You remember how the signal, the peak amplitude varies on both the positive and a negative equally on an AM modulated signal. All right. Let me just go up to the top here. What item of test equipment contains horizontal and vertical channel amplifiers? An ohm meter, a signal generator, an ammeter, or an oscilloscope? Hey, that's a good one.
The one that costs
plenty of clues on that one.
the one that costs $200.
Yes,
D.
that's it. That's it, guys. Number D. All right, that would be it. Number D is correct. See, by show and tell, you actually remembered that by me showing you a picture of mine. Okay, the next one. Which of the following is the best instrument? And you got your guy wire, when checking the keying waveform of a CW transmitter? An oscilloscope, a field strength meter, a side tone monitor, a wave meter?
Alpha.
I'm going to say oscilloscope again.
Yes. Oscilloscope. Okay. Oops. Was that was the one, right? What signal source is connected to the vertical? This is the one we had. Which of the following it takes advantage of? I'm trying to find the last question I had. There. Is that the last question?
Yes,
That's
sir.
the next new question.
This is the next new question. Which of the following is the best instrument to use when checking keying waveform? We answered that. Okay.
I'm sorry. No, my bad.
Yeah, I just got out of sync. I just want to make sure I was the right one to do here. Hold on a second. I can move it up to the top. Okay. What signal source is connected to the vertical input of an oscilloscope when checking the RF envelope pattern of a transmitted signal? The local oscillator of the transmitter, an external RF oscillator, the transmitter balanced mixed input, the attenuated RF output of the transmitter. What signal source is connected to the vertical input of an oscilloscope when checking the RF envelope pattern of a transmitted signal? The local oscillator of the transmitter, an external RF oscillator, the transmitter balanced mixer output, or the attenuated RF output of the transmitter. What would you suggest?
I'm guessing delta, but I'm not sure.
Okay, now
yeah, delta.
In this question, the answer is a dead giveaway in the way the question is asked. When checking the RF envelope pattern. So the attenuated RF output of the transmitter is the only one that can meet that question. And my answer would be D.
Spidey sense comes in handy.
Yes. So in that one, you can find the answer actually in the question. A lot of them are not that easy. Which of the following is an advantage of an oscilloscope versus digital voltmeter? An oscilloscope uses less power. Complex impedances can be easily measured, or input impedance is much lower. And D, complex waveforms can be measured.
Delta.
Delta.
Delta. Anybody else out there?
I'm thinking delta too.
All right. And you guys are right. Okay. Are we doing good so far? You know, we don't have too much more to go, I don't think.
I'm good.
I'm good.
Yeah, I'm good.
Okay. Why is a time delay sometimes included in a transmitter keying circuit? And remember those little waveforms I was talking to you about, and in this particular one, maybe it'll come back to mind. To prevent stations from interfering with one another. Let me go over to the main screen here so we can all see it better. To prevent stations from interfering with one another, to allow the transmitter proper regulators to charge properly, to allow time for transmit receive changeover operations to complete properly before RF output is allowed, to allow time for warning signals to be sent to other stations.
Charlie.
Charlie.
How about anybody else out there?
Charlie.
And then that is correct. You remember that. You remember that when I was covering that. That was a good one. Okay. What is the reason for neutralizing the final amplifier stage of a transmitter? For neutralizing, to limit modulation index, to eliminate self-oscillation, to cut off the final amplifier during standby period or to keep the carrier on frequency. What is the reason for neutralizing the final amplifier stage of a transmitter?
Bravo.
Bravo.
Yeah, you remember, and I believe that is also correct. And remember that we were talking about that self-oscillation thing. Okay. What is the name of the process which changes the instantaneous frequency of an RF wave to convey information? Frequency convolution, frequency transformation, frequency conversion, or frequency modulation?
D.
Delta.
Everybody out there, anybody else?
I agree. Delta.
D. Correct. And you remember that one. That's good. I guess I spent a lot of time on those things when we were covering the actual details. I'm glad I did, because some of that stuff comes back to mind. Does it not?
Mm-hmm.
Yep, it does indeed.
It does.
Okay. What is the stage in a VHF FM transmitter that generates a harmonic of a lower frequency signal to reach the desired operating frequency? A mixer, a reactance modulator, a pre-emphasis network, or a multiplier? Now, look at the question carefully. What is the stage in a VHF FM transmitter that generates a harmonic of a lower frequency?
Delta.
And anybody else would like to guess on that? Okay.
No.
And D is correct. The harmonic is something that is multiplied. A harmonic is a multiple or submultiple, a subharmonic of a particular frequency, and definitely multiplier is correct. All right. What is the total bandwidth of an FM phone transmission having a 5 kilohertz deviation and a 3 kilohertz modulating frequency? Well, I knew that was coming. I don't remember the formula myself, but I think the 5 kilohertz was part of that discussion we had, and it's a 5 kilohertz deviation and a 3 kilohertz modulation. There's that formula in your mind.
Delta.
5 plus 3 times 2.
5 plus 3 is 8 times 2. If you remember that particular formula, 5 plus 3 times 8 times 2, and you say it is
D.
D and delta. And that would be correct. Okay, what is the frequency deviation for a 12.21 megahertz reactance modulated oscillator in a 5 kilohertz deviation of 146.252 megahertz? And that's, what is that formula? 5 plus 3 plus times 2, but there's a square in there. What would you guess?
This formula is, but just memorize the question and answer.
Yeah, you got to almost memorize the thing.
It's B, but only because I remember.
Yeah.
Yep, B.
Yeah, and it's a 5 plus It's not 5 plus, it's a square of something. Anyways, you've got to remember that one. I wish I could say 12.2 times 146. It doesn't come out that way, but I believe it's B also. Yep. These several are tough questions, and those are the ones you really got to also focus on as well when you're trying to go through these questions again by yourselves. And taking the test like this is great. And by the way, the test that I'm giving you is not going to be the questions that you'll get on the test. So keep that in mind.
Actually, I think they are.
Well, they randomly choose them. So how can you say that? 100%?
They're in the pool. In other words, they're not going to necessarily all be, but they could be.
Yeah. I'm just saying that these are not the exact questions you're going to get on your test. They may be including some of them, but there'll be others involved. I've been through enough testing now to know that they don't come up that way. I can guarantee you. So maybe the result is you got to take all of the questions that are in the pool and try to keep them in mind. If there's 300 of them, you got to go through 300 of them and try your best to remember what's going on, because they'll mix them up. What emission is produced by a reactance modulator connected to an RF power amplifier stage? Multiplex modulation, phase modulation, amplitude modulation, or pulse modulation?
Bravo.
Yep, bravo.
What emission is produced by a reactance modulator connected to an RF power amplifier? And the answer is B as well. Remember, we were talking about phase modulation. And, it's not clear. I don't think I made it clear to you about what phase is, but if you remember a circle that has 360 degrees, and remember a standard waveform, a sine waveform up and down, and then tilt it in your head, going back into the page, and you tilt it 45 degrees, that's a phase angle. And indeed, we can modulate the phase and actually get intelligence out of it. Okay. What is the name of the process that changes the phase angle of an RF wave to convey information? Phase convolution, phase modulation, angle convolution, and radiation inversion. This is pretty easy. And your answer is?
Bravo.
Bravo.
Everybody agree out there?
Yeah. Bravo.
Yep.
Yep.
Okay. And phase modulation pretty much stands out on its own. When you remember that sine wave that I showed you and you tilt it, anything associated with that in your mind would be phase modulation. So, keep that in mind. A picture is worth 1,000 words. How is the efficiency of an RF power amplifier determined? Divide the DC input power by the DC output power. Divide the RF output power by the DC input power. Multiply the RF input power by the reciprocal of the RF output power. Or add the RF input power to the DC output power. What would you say?
Bravo is a guess.
Yeah, bravo.
Bravo.
I say to understand efficiency, RF power amplifier, in order to do that, you got to know what the output power of the thing is, and then divide it by the input power. That's the only way I know in my mind is to remember that. The output over the input. Okay. Okay, what is the output peak envelope power, that's PEP, from a transmitter if an oscilloscope measures 200 volts peak to peak across a 50 ohm dummy load connected to the transmitter's output? What is the PEP? 1.4 watts, 100 watts, 353.5 watts, or 400 watts? What is the output PEP of a transmitter if an oscilloscope measures 200 volts peak to peak?
B.
B.
Bravo.
Bravo. 200 volts peak to peak. Bravo. Exactly. Remember that 100 watts. And there'll be another question coming up talking about decibels, I would think. I would hope, because that's tricky. Okay. What is the ratio of peak envelope power to average power for an unmodulated carrier? 0.707, 1, 1.1414, or 2?
Bravo.
Bravo.
What is the peak envelope power to average power of an unmodulated carrier? Everybody say B?
Yep.
And that is correct. That was a trick question because there is other ones that sound similar, I remember, and that 0.707 often comes up, but it's the average is 1. Okay, this one here. What is the output peak envelope power of an unmodulated carrier if an average reading watt meter connected to the transmitter output indicates 1,060 watts? What is the output peak envelope power of an unmodulated carrier? 1,060 watts.
Is this a trick question?
I think it is.
Because going back to the one, unmodulated.
It's output of an unmodulated carrier. Now, obviously, the carrier, in order to read it of an unmodulated carrier, you couldn't do that with single sideband because there'd be no carrier if nothing's unmodulated. You don't talk, there ain't no signal.
I say alpha.
Well,
530 watts. Now, how did you arrive at that? Just by guess?
So I remember what we discussed, and I recognize this question, and I remember what the answer was.
Okay.
That always wins.
And you say it's A.
I still guess B just because of the unmodulated, but it could very well be it.
It is B. And that's exactly right, because the unmodulated signal, it represents a carrier. It has to be a AM carrier. It has to be a carrier by itself, which is an AM type carrier. Because if you have any power of an unmodulated carrier, you turn on the transceiver and it's AM, you're transmitting a carrier. And then you modulate the amplitude of that carrier. So since it's unmodulated, it's going to be the same.
Oh, yeah.
As the indicated power in watts. Yeah. Okay.
I think you skipped one.
Oh, I did? Oh, yeah. Let's see. This was yeah, thank you. Boy, those are good eyes out there. Okay. What dB change represents a factor of 2 increase or decrease in power? Approximately 2 dB, 3 dB, 6 dB, or 12 dB? What dB change represents a factor of 2?
Bravo.
I go with Bravo as well.
What about anybody else out there?
Yeah, I'm leaning Bravo too.
Okay. And you'd be right. All right. I knew they'd get to dBs. How much must the power output of a transmitter be raised to change the S-meter reading on a distant receiver from S8 to S9? That's 1 dB. Approximately 1.5 times, 2 times, 4 times, or 8 times?
4 times.
4 times.
Yeah,
Charlie.
4 times.
That's
Charlie.
right. You got it. Remember that one?
Yeah,
I
good
showed
luck
you
with that.
I showed you my meter, and I showed you the actual signals coming in. 1 dB change requires 4 times the power. And remember, I told you can also get it by increasing the gain of your antenna by X number of times, and that will also increase the signal. It does not necessarily have to be the RF transmitter output power. That's a brute force way of doing it, isn't it? If you have a very inefficient antenna, and I increase my power to increase it from S8 to S9, I got to go from 100 watts to 400 watts. I would prefer to experiment with the antenna before I bought a power amplifier. That's a lot of money. Antennas are a lot cheaper.
So if I understand this correctly, the higher the gain antenna you have, the better it is.
Yes, that's right. And it will increase the receiver's S meter by X number of dB gain. And now, I mean, just increasing it by 1 dB, you can hear it. You can hear it, and that's a nice increase. It isn't an end all be all. Like if you had an S0 signal, you could still hear the signal if the noise wasn't very bad. But just think what would happen if I could raise it just 1 more dB. I'd be at S1. I'd be heard a little better. And if the noise was a little louder, I could overcome that excessive noise. So yeah, a good efficient antenna is oftentimes the best way to go to get your signal out. Not necessarily spend a lot of money on a power amplifier. How does a signal that reads 20 dB over S9 compare to one that reads S9 on a receiver, assuming a properly calibrated S meter? This one, you're going 20 dB.
Delta.
Delta.
Yeah. Delta is 100 times stronger, and that would be correct. Okay. For which of the following modes is a Class C power stage appropriate for amplifying a modulated signal?
Bravo.
You guys are fast. FM, AM, or all of the answers above. And you say Bravo?
Correct. Bravo.
Everybody out there say something else?
I like Bravo.
Bravo.
I agree.
You remember that? Only Class C was for FM for its efficiency. All right. Which of these classes of amplifiers has the highest efficiency? Class A, Class B, Class AB, or Class C?
C, senor.
B is in Baker?
No, D is in Charlie, Class C.
D.
B is in Delta or dog or whatever.
Delta.
That's correct. Well, remember, we covered that in the question period there, that's for sure. Okay. We're almost down to the bottom, guys. All right, which of the following describes a linear amplifier? Any RF power amplifier used in conjunction with an amateur transceiver, an amplifier whose output preserves the input waveform, a Class C high efficiency amplifier, an amplifier used as a frequency multiplier.
Bravo.
Linear amplifier.
That is going to be B.
Yep,
Bravo.
bravo.
In other words, you're saying that the word linear means even, straight across, or whatever. And you would be right. All right. What is the correct adjustment for the load or coupling control of a vacuum tube RF power amplifier? The correct adjustment for the load. Minimum SWR on the antenna, minimum plate current without exceeding maximum allowable grid current, highest plate voltage while minimizing grid current, and maximum power output without exceeding maximum allowable plate current. What is the correct adjustment for the load or coupling control of a vacuum tube amplifier? What do you guys say?
D.
Yeah, D, Delta.
D is in Delta. And it's not Baker, minimum plate current
Nope.
without
Delta.
exceeding maximum allowable good current. Okay. You guys are right on the money because it is D. Remember, maximum power output, you cannot exceed the plate current because you will start to distort the signal then. So you want maximum. That's the only place to get is maximum power output is measure the plate current and make sure that you got maximum allowable plate current. And last but not least is what reading on the RF current meter of a vacuum tube RF power amplifier indicates correct adjustment of the plate tuning control? Correct adjustment of the plate tuning control. What reading on the plate current meter? A pronounced peak, a pronounced dip, no change will be observed, a slow rhythmic oscillation. And your answer is
Bravo.
Bravo. Remember that, dip in plate current. And that is bravo. Okay. Wow. We're at the end. We're at the end of that setup. You still see my you still see my screen?
Yep.
Okay.
Yep.
Well, what did I cover? I covered chapter
chapter 10, your HF transmitter.
Yeah, chapter 10. And I'll close this out here. And screen sharing is stopped. Let me just, I'm just going to stop it for a second here. And the next one, gee whiz, I've got a whole bunch to cover. I'm supposed to cover chapter 10, 11, 12, and 13 and 14. That's an awful lot to cover. Are you guys wanting to take a break?
I would like to.
Yeah, that'd be nice.
Yeah, go ahead. Let's take a 10-minute break. I need to go down anyways and get a cup of coffee.
Great.
And you guys out there, anyone else, go ahead and take a 10-minute break. Okay, guys?
Sounds good. Thank you.
And we're going to take a break here too. So I'm going to mute that feed. Okay. Hopefully that was some complicated stuff. Some of it was. Anyway, it's going, I think it's going pretty well though. Some of it can get kind of dry, but you've got to just kind of power through it and see what kind of information you need to memorize, see what kind of information you need to brush up on. He did a good job of explaining what it meant. He went through all. I think the reason the question part took so long is because he went through all of them. I don't think the previous presenters have done that. But let us know in the chat how you're doing. Let us know if you do have any questions while he's going along. Put them in the chat if you're watching on YouTube, and I can relay them back and forth. I'm up and down and in and out. I've been sitting here most of the morning. I got up and got my coffee refilled a couple of times. Other than that, I've been here this morning. So, but do let us know if you have any questions that come up in the chat. So that is where we are. So we got about a 10-minute break. Everybody go ahead and get up and stretch. Go get something to drink. Go get something to eat, depending on what time zone you're in. And he got up about 10:45 a.m. Texas time, so I'm going to guess about 10:55, maybe right at 11, he's going to start back again. And I assume he'll go till about noon, maybe a little bit after, and then we'll take a lunch break for about an hour there. So they finished around 11 a.m. last Saturday. I don't know if he said he's got some more to go, so I don't know how long all that's going to take or what they have planned after lunch today. But we'll stay here and we'll keep streaming the whole thing, and we'll just let them teach their course. So once again, thanks for being here today. Do hit the thumbs up button on the YouTube video if you don't mind, if you haven't done that already. Looks like we got about 25 watching now. And it is a good thing for people to get upgraded to general. Be sure and check this channel. Oh, somebody asked earlier. Hold on, let me go find. I am going to go find the playlist for this series. Somebody asked earlier, where was parts 1 and 2? And the answer to that is on a playlist on my channel that I created last weekend. Playlist. There it is right there. I'm going to share that in the chat right now. So if you missed last Saturday, they taught the session all day. The live stream went all day. I split it up into 2 sessions because there was about a 90-minute lunch in the middle. So I did session 1 in the morning, session 2 in the afternoon. This is session 3, as it says on, it's titled Part 3 on YouTube right now. But that playlist that I just shared a link of in the chat is where you can find parts 1 and 2 from last weekend. Once it's all said and done, after this will be the last, probably parts 3 and 4, I assume. Anyway, they're supposed to finish today. Once it's all said and done, I might take the 4 parts and kind of split it up and take out all the live stream stuff and just take the class pieces and put them into different episodes up on the channel, probably in the same playlist. Might call it like a condensed or Reader's Digest version or something like that. I don't know. And post that there for people to watch if they don't want to watch the whole live stream replay and everything like that. So Steve, thanks for being here this morning. Nikki from Ireland, thanks for being here this morning. Thanks for commenting today. Good deal. Okay, so we're going to, once again, this is break time. Everybody stepped away for a minute, so we're going to give everyone a chance to get up and stretch or get something to drink or whatever. So we'll be back here in just probably about 5 minutes or so. Okay, we're just about back, it looks like. Oh. Okay, John. No worries there. Thanks for being here. Subnetting is all messed up. You gotta love that. Rebooting the router. Okay, it's been about 10 minutes.
All right, everybody.
All right, we're gonna
if
get back to it.
If you can hear me, we should probably get back to unmuting your microphones.
Yeah, I'm here, ready to go.
Okay.
We're good here.
Okay, and Tim, K5TGS, got your speaker, your microphone unmuted. Okay. Before I share my screen, let me just make sure I got the right session up. Okay. This next one is okay. Okay, is everybody back online now? Do you see the lesson here?
Yep, I do.
Okay, this is going to be about the receiver. Let me take a little roll call. There's what, 6 people? I think there's 6 people. Okay, I can't see you right now because I got the full screen view. Is everybody back?
I'm here.
Yes.
Okay, I hear 2 people. How about a third person? As I know, I see him on the screen. Okay, I'm going to go ahead and begin. So this one's about receivers. Passing the C, okay, your new general bands, FCC rules. We've covered this part. This is a digital, okay. And here we are. We're on your receiver. This is what we're on. And the others, 10, 11, 12, 13, and 14, I believe I cover these 3 after the receiver. So we do have to move along if we're gonna, unless you guys have time. I mean, I'm here for as long as you want, but I don't want to shortchange anybody. So the receiver, the simplest combination of stages that implement a super heterodyne receiver is an HF oscillator, a mixer, and a detector. So this is the oscillator, this is the mixer, and this is the detector. And this dotted line represents the front end of the receiver. You got to have an RF amplifier to amplify the signal from the antenna. And it goes into this mixer, because it's feeding, an oscillator is feeding into it, and the output is whatever is the RF signal is then mixed with the, then mixed with the oscillator, and the output is less than the signal that's coming in, the sum of the mixed signal. That's how you can change the way the get the waveform. Get the information from the RF amplifier and bring it down to a level that the receiver can deal with. In this case, being a super heterodyne, this is the method that is used. And it goes into an IF amplifier. It amplifies the signal as the resultant signal, and then the receiver's passband signal is detected from that IF signal, and then it goes to the baseband amplifier to the speaker. Baseband amplifier obviously would be the audio amplifier. Then we go, this is another block diagram, the RF stage, and it's pointing to some hardware here. This is the actual capacitor, a gained capacitors. In this case, they're showing 3 capacitors and a knob that you turn. And it's going to be set up here in the mixer signal. I wonder if I should, let me see here, if I can do the slideshow thing. Maybe I can do this slideshow without having to.
I suggest you try to click on begin from the beginning.
Yeah. Now, yeah, from the beginning, yeah, maybe that's what caused the thing to not work properly, is the way I set it up. Let me go back to that and go to the beginning and hold on a second, slideshow. And I'll say from beginning there, and I'll just scoot down.
Yeah, that didn't work either.
Yeah, this is going to work, I think, this time. Yeah, this is much better.
But we still see the presentation slides yet where you can edit it and change things.
Oh, you see that? You don't see my screen? It's a big screen. I mean, everything is, I don't see that on mine, but you say you see the slides on the side?
Correct.
Uh-oh. I'm not sure what's happening there because my screen shows the, the video. Okay, so
I think if I can make a suggestion, if you uncheck the box that says use presenter view, uncheck that box and see if that would help. It's over where it says monitor. Yep.
Oh, use presenter view. Oh, maybe that's it. Okay, now let's try it and see. What do you see there?
Now I see the full screen of the power slide.
Okay, that was what it was. It was in the present. Thank you.
You're welcome.
So rare I use these PowerPoint presentations. I forget. Years ago, I used to use them all the time. Let me go back to the one I got here that we were covering. We went through this one. Okay, we were on this one here.
Yep, it's a lot clearer too now.
Yeah, a lot clearer. That's very good. In my picture there, yeah, it's fair. It's fair. I can see it. So that's the block diagram of the receiver, and the tuning capacitor would be in the mixer stage. There's the HF oscillator, and there's the mixer, and there's the detector, and the simplest combination. A mixer in AM broadcast receiver is a signal 800 kilohertz or 1200 or at 1200 kilohertz. That's the station signal. That's an AM, obviously an AM broadcast could being down that low. Signal B is at 1255 kilohertz or at 1655 kilohertz. It's a local oscillator. And the signal C at 455 kilohertz is the intermediate frequency. That's what the mixer will give you when you look at what's coming in and the signal that's being coming from the oscillator, and that's the signal that comes out of it. 455. A mixer is the circuit used to process signals from the RF amplifier and local oscillator and send the result to the IF filter in a super heterodyne receiver. So there's the mixer, there's a single conversion IF filter stage. These are IF amplifiers that filter the signal. And then down here is a dual conversion transceiver. A dual conversion, what they're trying to show here is two types or two versions. One's a dual and one's a single conversion. This down below is a dual conversion. And it's got a first IF, a mixer, and a second IF. This one up at the top only has one IF. Okay. And intermodulation is a process that combines two signals in a nonlinear circuit or connection to produce unwanted spurious outputs. In a receiver, intermodulation is necessary and desirable. It makes frequency conversion work. Undesirable when a strong station mixes with a weaker one in the receiver's front end. The circuits used to combine signals from an IF amplifier and the BFO, that's called beat frequency oscillator, is a product detector and sends the result to the AF amplifier in a single sideband receiver. And here's a single sideband /CW receiver where you have the RF amplifier, the mixer oscillator is the same, a filter, IF amplifier, and then the product detector, and then goes into the speaker. This is this thing here. Oh, that's just my gizmo there. And it goes into the speaker. So the IF amplifier is there. The beat frequency oscillator is there. This is the beat frequency oscillator that beats against the incoming IF signal, which the beat is a product detector. And that product detector is there that takes that the IF signal and the beat frequency oscillator signal and produces from it the audio signal that the AF amplifier has. The AF amplifier. Okay. Heterodyning is another term for mixing of the two RF signals. The oscillator, oscillator 1, oscillator 2, and a mixer. So you can take two signals and mix them into the mixer. In a receiver, the mixer stage combines a 14.250 megahertz signal, that's in the 20 meter band, input signal with a 13.795 megahertz local oscillator signal to produce a 455 kilohertz intermediate frequency IF signal. So the difference between 14.250 and 13.750 is a 455 kilohertz. And a mixer circuit is used to process signals from the RF amplifier and local oscillator and send the result to the IF filter in a super heterodyne receiver. So there's incoming signal from the antenna. The mixer looks at that, looks at the local oscillator, and comes out with this 455 kilohertz signal that the rest of the circuitry can handle. In this mixture, the output is the sum and the difference of the two amplified signals, the sum and the difference. The sum would be 14.250 plus 13, or 28.5 megahertz. And the difference is 14.250 minus 13, or 455. So keep in mind, there's two things going on here, sum and a difference, in order to get the 456 out. Filtering removes the undesired frequency. Recap a block diagram of dual conversion receiver. The dual conversion receiver has an RF amplifier, RF filter, RF amplifier, a mixer, a local oscillator, first IF amplifier, and another filter, second mixer, first mixer, second mixer, and second IF amplifier. In a single super heterodyne, the second mixer and second IF amplifier are removed. So we're looking at a dual conversion. Dual conversion means it's got two mixers and two IF amplifiers. Passband functions, amplifier signals, process signals, passband amplification. Receiver can now more finely tune the desired frequency, and passband amplifier recovers the info in the demodulator and then the amplified signal goes to the audio amplifier. That's typically what a dual super heterodyne receiver is. A high stability variable frequency oscillator in a transceiver is a typical application for direct signal synthesizer. Without these highly stable oscillators, your frequency would waltz around across the band or jump randomly around the band. Variable frequency with the stability of a crystal oscillator is a major advantage of direct digital synthesizing, DDS, direct digital synthesizer. Digital works on the air with tolerances down to 1 hertz, and it keeps your signal stable on a frequency, making reception of this digital signal more reliable. And can you still see me?
Yep.
Okay. I'll look at this, and I want to show you what the signal looks like here. Okay. Now, you see this, can you all see this 14305.000? Can you see that?
Yes.
Yep.
So watch when I make the tuning. Watch this last digit. This is 1 hertz, this last digit, and I'm able to move it by 1 hertz, see? Now I'm moving it slow as I can do it, but I can do it. See, 1, 2, 3, 4, 5, 6. So in effect, because of this, the beauty of this particular transceiver, I'm able to move it in increments of 1 hertz. If I wanted to move it 10 hertz, I'm able to do it digitally by just simply touching the there. So now I'm moving it in 10 hertz increments. Okay. So I can do this with this type of receiver. And now I'm back to 1 hertz. So with that in mind, in the second IF stage, you get a much more refined signal adjustment. Digital work on the air with tolerances down to 1 hertz keeps your signal stable on a frequency, making reception of digital signal more reliable. And for sure on that. The term software-defined radio. By the way, this one is a software-defined radio. I want to call your attention to it again. That's a software-defined radio. You see the waterfall display? You guys all see that?
Yep.
Those are all signals on the waterfall display that are coming in. So if I tune it, you can see my tuning knob. Put up a little more gain for you. And if I'm right on his frequency, that means I've got the cleanest audio that I can get out of his carrier. Let's go to, they're jumping all over the place. As you can see, there's all kinds of signals. Now this guy is operating on 14228.500. He's not on a 1 kilohertz separation. It's okay. But you can see now that I am with a software-defined radio, I get a waterfall display like this. And there's a lot more involved in a software-defined radio than a super heterodyne. And this is the modern way in which transceivers are being built today. At least a lot of them are, such as Flex Radio. And ICOM makes a software-defined radio, and so does Yaesu now. And sometimes they'll mix the two. So we're going to talk about software-defined radio. It means a radio in which most major signal processing functions are performed by software. Software-defined radio is a radio communication system where components that have been traditionally implemented in hardware, e.g. mixers, filters, amplifiers, modulators, demodulators, detectors, are instead implemented by means of software. Oh, wait a minute. And believe it or not, this is a software-defined radio. An advantage of using an I and Q signals in a software-defined radio is that all types of modulation can be created with approximate processing. And there again, you see that in this case, this looks to me like a flex radio. That's the brand, similar to that. A software-defined radio is one that can be configured to any radio or frequency standard throughout the use of software. An SDR radio is a radio communication system where components that have typically been implemented in hardware, such as mixers, filters, amplifiers, detectors, are instead implemented in software. That's a repeat. There is a 90 degrees phase difference between an I and a Q signal that software-defined equipment uses for modulation and demodulation. And the combination of a mixer's local oscillator and the RF input frequencies produce the sum and difference of the output. If a receiver's mixer is at 13.800 megahertz VFO with a 14.255 megahertz received signal to produce a 456 kilohertz intermediate frequency signal, a 13.345 megahertz signal will produce an image response in the receiver. And it goes on, 13.8 megahertz minus 455 kilohertz is 13.345 megahertz, the lowest image response frequency. To prevent this, many receivers use a tuned preamplifier before the mixer input, sometimes called a preselector. An advantage of a receiver digital signal processor, IF filter, as compared to an analog filter, is that a wide range of filter bandwidths and shapes can be created. You know what they're talking about here is in the software-defined radio, compared to a hardware or analog filter. These filters can be created within the software. As the noise reduction control level in a receiver, that thing is in my way, I can't read it. It receives a signal may become distorted. One reason to use the attenuator function that is present on many HF transceivers is to reduce the signal overload due to a strong incoming signal. Attenuator function. The attenuator function would be the RF attenuator. And again, I can show this by example here. Can you see that now? When I reduce the RF gain of the signal, watch what happens. See that? It all kind of goes away. And I can get it to a point where they just begin to peak on the waterfall display. See how they are now? You guys see that okay?
Yep.
Okay, so that's the RF input, and that's what they're talking about here. So I'm bringing it up to its maximum point without full distortion. Okay. This is a dual function switch, a preamplifier. They're telling you here that there is also, and I could have shown you my switch here on my radio, but it's a preamp, and it's an attenuator. In other words, I can attenuate the signal or I can amplify the signal. Once it gets set by the RF amplifier, the RF gain control, then I can also use that. A noise blanker is a device that detects pulses and blocks the signal during the time of a pulse. A noise blanker becomes more effective, very much effective at large bandwidths, as long as there are no strong signals present in the passband. The noise blanker, it could be cars passing by your house with click, 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 that kind of noise, or low frequency noise being generated by something in the house. The button that's on my receiver transceiver here is a noise blanker, and I can adjust it so that I can tailor it to the incoming noise that I'm trying to get rid of. And once I do that and I adjust it properly, the noise disappears. The purpose of the notch filter found on many HF receivers is to reduce interference from carriers in the receiver's passband. I don't know if they're going to show you guys an example of that with a notch filter, but I'd like to show you a quick example because these things will stick in your mind if I do them this way, and I know we take a little bit more time. Okay, tell me, can you all see the screen that I'm pointing at?
Yep.
Okay, I'm going to turn on a kind of a notch filter. See that one that's coming up? Okay. Now, if I want to, let's assume I've got a signal here. If I can make it. I'm going to tune it in such a way that I could probably demonstrate it. Okay, now there's some background noise there. So if I want to, I can take my notch filter. See, I can tune it left or right. And if necessary, see, I can almost cut out that carrier. Or if I had a signal that was very close by that carrier, I could see it. And I could then adjust it out so that that little notch, what you see in that orange area, that's the only signal my receiver will hear is in that area. So if I've got a carrier next to him within maybe two kilohertz, there's a good chance I can notch him out by adjusting this in such a way. So I've got lots of control over that kind of a signal coming in that interferes with another signal. So that's what they're talking about, a notch filter. And any of your software-defined radios these days, they have them, and so do the super heterodyne type amateur radios have them too. And a lot of them are very good. So, and those are some of the things you're going to want to look at in terms of effectiveness by the manufacturer. A super cheap radio won't have as good a notch filter, believe me. Okay, so this is typically what I just showed you. If you remember, I was trying to show you, here's a signal in this case, and here's two carriers either side of it. I can notch out just that signal. I can notch it so just that signal is in the passband. Here's an example here where we have the QRM on this one, and we have the signal we want to hear. We moved my notch filter out of that area, and it eliminates this one, but still gives me the signal coming in. So doesn't that equate to what I just showed you? It's kind of like that. So you can notch it, and you can move things around. So this is a very handy feature for the notch filter, notching out signals that you don't want to hear. And in effect, that's what it does. This is in frequency in the 2 kilohertz area. You would, in this case, be able to notch out that frequency that is affecting you, that you want to get rid of. A discriminator circuit is used in many FM receivers to convert signals coming from the IS amplifier to audio. FM receivers have different types of circuits than the super heterodyne receiver designed for AM, CW, and single sideband. FM receivers has the IF input and transformer coupling with capacitive coupling from here and transformer coupling. And it goes in here and it gets filtered and produces an output audio. A lot of theory in here, but too much we can go through here. But just remember, a discriminator circuit is used in many FM receivers to convert signals coming from the IF amplifier to audio. So IF to audio is a discriminator. And this will be the output voltage and the frequency. The S meter on your new HF transceiver ties directly to the receiver section of the radio and is tied into the receiver's automatic gain control, AGC, automatic gain control. Do not confuse that with automatic level control. Automatic gain control. The S meter is an instrument present on the majority of radios, and I've shown you that on mine, that measure the signal strength of the signal. Most all receivers have an S meter showing received signal strength. And here's a typical thing. These are analog signal strength meters. They also show by their different scales, power, SWR, compression, audio compression, and so forth. This scale over here on the left just shows S meter and power. So there's a switch that switches between S meter reading and power. Same over here. Let's see, valid through, what is that all about? Okay, all right, we're gonna go through a test here, huh? What is the simplest combination of stages that implement a super heterodyne receiver? RF amplifier, detector, audio amplifier, RF amplifier, IF discriminator, HF oscillator, mixer detector, HF oscillator, pre-selector, audio amplifier. You want time to think about that? What is the simplest combination of stages that implement a super heterodyne receiver? An RF amplifier, a detector, and an audio amplifier, or an RF amplifier, a mixer, an IF discriminator, or an HF oscillator, a mixer and detector, or HF oscillator, pre-scaler, audio amplifier. What would be your thinking on this?
Charlie.
Charlie.
HF oscillator, mixer detector. HF oscillator, what is the simplest combination of stages that implement a super heterodyne receiver? And that would be C. Okay, now if I press it again, I should go to the next question. Yes, okay, we're on sync. And that presentation control was what caused me the problem last time. This is good. What circuit is used to produce, to process signals from the RF amplifier and local oscillator and send the result to the IF filter in a super heterodyne receiver? A balanced modulator, an IF amplifier, a mixer, or detector? And the answer is?
Charlie.
Yeah, Charlie.
You guys agree out there? Everybody?
Yes, sir. Couldn't quite unmute myself.
Okay. All right, that's a mixer. What process combines two signals in a non-linear circuit or connection to produce unwanted spurious outputs? Intermodulation, heterodyning, detection, and roll-off or roll-off. It combines two signals in a non-linear circuit or connection to produce unwanted spurious outputs. And your answer is?
I think A.
Yeah, so I was leaning
Alpha.
more
B.
towards is A, alpha.
And who says B? Somebody say B?
I'm thinking is B.
I was thinking A or B, but
It's A, intermodulation. So it's a nonlinear circuit. Intermodulation is nonlinear. It's a combination. Intermodulation means to, combine a signal and modulate it. Okay. What circuit is used to combine signals from the IF amplifier and the beat frequency oscillator and send the result to the AF amplifier in a single sideband receiver? An RF oscillator, an IF filter, a balanced modulator, or product detector?
D, delta.
Anybody say delta? Everybody says delta?
Yeah.
You're right. What is another term for the mixing of two RF signals? Heterodyning, synthesizing, cancellation, or multiplying?
A.
Yeah, A, alpha.
That would be correct. Heterodyne, combining two signals to produce something else. Okay. Which mixer input is varied or tuned to convert signals of different frequencies to an intermediate frequency? An image frequency, a local oscillator, an RF input, or a beat frequency oscillator? Well, which mixer input is varied or tuned to convert signals of different frequencies to an intermediate frequency? An image frequency, a local oscillator, an RF input, or a beat frequency oscillator?
I think D.
Yeah, so do I.
Is that Baker or D as in
Delta.
dog?
Delta.
Delta? No, it was B. The local oscillator is the first one that shows up in the chain, if you remember, and goes into the mixer.
Oh yeah, that's right.
Yeah. Which of the following is a typical application for a direct digital synthesizer? A high stability variable frequency oscillator in a transceiver, a digital voltmeter, a digital mode interface between a computer and a transceiver, a high sensitivity radio direction finder. Which of the following is a typical application for a direct digital synthesizer?
A, alpha.
A. Alpha.
I believe you guys are right. Everybody agree with that? I'm not saying you're right or wrong, but yes, it is right. Which of the following is an advantage of a direct digital synthesizer, DDS? Wide tuning range and no need for band switching, relatively high power output, relatively high power consumption, variable frequency with the stability of a crystal oscillator?
Delta.
Delta.
Yeah, delta.
Okay, that is correct. What is meant by the term software-defined radio, SDR? A radio in which most of the major signal processing functions are performed in software. B, a radio provides computer interface for automatic logging of band and frequency. A radio that uses crystal filters designed using software. A computer module that can simulate performance of a radio to aid in the design process.
A, alpha.
Alpha.
Aha, and that is correct. That's in my SDR radio here. Okay. What is the advantage of using an I and a Q signals in a software-defined radio? The need for high resolution analog to digital converter is eliminated. All types of modulation can be created with appropriate processing. Minimum detectable signal level is reduced. or converting the signal from digital to analog creates mixing products. I and a Q signal.
Bravo.
Yeah,
All
bravo.
types of modulation can be created with appropriate processing. Advantage of using I and Q signal, and the answer is correct. It's a B. Remember, we were looking at that diagram that showed the I and the Q signals that are used to detect the phase and the amplitude. What is the phase difference between the I and the Q signals that software-defined radios equipment uses for modulation and demodulation? 0, 90 degrees, 180 degrees, or 45 degrees?
It's 90, right?
That's what I'm thinking.
You're right. 90 degrees. That's exactly right. And you know, I want to press the term phase. You know what it means now with a circle, 360 degrees, or a sine wave that's on the page in two-dimensional, and you'll tilt it, you know, toward the page, and it tilts forward or backwards. That's the phase that we're talking about. What combination of a mixer's local oscillator, LO, and RF input frequencies is found in the output? The ratio, the average, the sum and difference, the arithmetic product.
Charlie.
Charlie.
Yeah,
Pomp and
Charlie.
circumstance.
And you guys would be right. Sum and the difference. If a receiver mixes 13.8 megahertz VFO with a 14.25 megahertz or 225 megahertz received signal to produce a 450 kilohertz intermediate frequency IF signal, what type of interference will a 13.345 megahertz signal produce in the receiver? A quadrature noise, image response, mixer interference, or intermediate interference?
Bravo.
Yeah, bravo.
A mixer interference will produce, let's see, what type of interference? An image response, which is B. That's correct. And that kind of thing. That's a tough one, especially 2 or 3 weeks from now when you try to remember it. So
3 days from now.
Image response is intermediate frequency. Image frequency, that's the way I'd remember it. And that would tell you image response. Which of the following is an advantage of a receiver DSP, digital signal processor, IF filter, as compared to an analog filter? Which of the following is an advantage? A wide range of filter bandwidths and shapes can be created. Fewer digital components are required. Mixing products are greatly reduced, and the DSP filter is much more effective at VHF frequencies.
Alpha.
Oh,
Alpha?
Anybody else guess?
I'm with Alpha too.
And you'd be correct.
No.
What happens as the noise reduction control level in a receiver is increased? The received signal may become distorted. Received frequency may become unstable. CW signals may become severely attenuated, and received frequency may shift several kilohertz. What happens as the noise reduction control level in a receiver is increased? You're trying to increase the noise reduction. Received signals may become distorted. Received frequency may become unstable. CW signals may become severely attenuated.
I think bravo.
Yeah, bravo.
May become unstable. Received signals may become distorted. Remember that noise reduction does affect the incoming signal because you're changing the way the received signal is heard. And so you got to be very careful with noise reductions so you don't affect the main signal. What is one reason to use the attenuator function that is present on many HF transceivers? To reduce signal overload due to strong incoming signals, to reduce the transmitter power when driving a linear amplifier, to reduce power consumptions when operating from batteries, and to slow down received CW signals for better copy. What does the word attenuator mean? What do you guys guess?
Well, it attenuates the signal, meaning it dampens it. To slow down.
Attenuation reduces, of course.
Right.
A, alpha.
Alpha.
Yeah, A, because as I showed you on my screen, as I raised up the RF gain, it's a form of attenuation, and I was able to, overload the waterfall display or make it look very, like it's not there. How does a noise blanker work? By temporarily increasing received bandwidth, by redirecting noise pulses into a filter capacitor, by reducing receiver gain during a noise pulse, by clipping noise peaks.
Charlie?
Do I hear anybody else?
Bravo.
By redirecting noise pulses into a filter capacitor. No, it is C. The noise blanker will clip or reduce or filter out the signal. So by reducing the receiver gain, so in effect, it reduces the gain for just that particular pulse, and making the receiver not hear it. What is the purpose of the notch filter found on many HF transceivers? Notch filter. To restrict the transmitter voice bandwidth, to reduce interference from carriers in the receiver passband, to eliminate receiver interference from impulse noise sources, to enhance the reception of a specific frequency on a crowded band. What would you say about this? Notch filter. Any guesses?
A.
To restrict the transmitter voice passband.
No. I say Bravo.
Showed us
Bravo.
Okay, anybody have anything else that they'd like to say? Okay, it's Bravo. Remember, a notch filter will cut out and make the receiver not hear it. What type of circuit is used in an analog FM receiver in analog FM receiver to convert IF output signals to audio? A product detector, a phase inverter, a mixer, and a discriminator. FM receivers now to convert an IF output signal to audio.
See, Charlie?
A mixer? You guys, anybody say anything else?
No. Mixer.
Okay. It's a discriminator.
Oh, yeah.
Remember that one? Yeah. Where is an S meter found? In a receiver, in an SWR bridge, in a transmitter, in a conductance bridge?
See, Charlie.
In a transmitter. Okay, everybody ready? A receiver. Remember, S meter receives signals. Yeah. If they would have said transceiver, that would have been a giveaway, but it is in a receiver. What does an S meter measure? Conductance, impedance, received signal strength, or transmitter power output?
That would be C.
Charlie.
Yeah, everybody agrees to that. Okay. Hey, is that it? That looks like that session. So what I got to do now is, that was short. So the next one is this one here. I'll share the screen again. Okay, and this time I've got to make sure, yeah, I've got to make sure that, let's see, slideshow. And yeah, I got that correct. So this ought to work good. Oscillators and components, okay. This is, okay, we got to go down here. Oscillators and components is the one we're on now. The basic components of virtually all sine wave oscillators are a filter and an amplifier operating in a feedback loop. So that's a transistorized oscillator. And you have the input signal here, and then this provides the feedback of the circuit that causes the thing to oscillate, and then you get an output here. Or you can, you could stop the oscillation in this. They don't tell you about this one right now, but this will cause the thing to oscillate with the proper resistance. Okay, and this is a typical sine wave that you might get out of an oscillator. A sine wave, a square wave, or a sawtooth wave, or I can't see it in blue. Yeah, it just says it's a different type of sawtooth wave. A sine wave, here we go. A square wave, a triangle wave, and a sawtooth wave. I couldn't see the triangle wave easily. The screen, it doesn't show it up, that deep blue color. The inductance and capacitance in a tank circuit determines the frequency of an LC oscillator. This is the inductance. These are inductors in various forms. And here's a capacitor, and this is a capacitor. This capacitor is a vacuum variable type capacitor, which I have out on my magnetic loop antenna that I use. And so this one rotates and has plates that go in between each other. There's a space between the plates. And this one has a bellows that moves in and out inside another bellows. And this would be, I guess what they're describing here is how it's connected in a circuit with a capacitor. The control grid is the element of a triode vacuum tube. Is used to regulate the flow of electrons between cathode and plate. Old school, these are vacuum tubes. This is the control grid here. This is a grid, and this is another type of grid, but this is a control grid. This is a secondary grid. Well, these go back, tetrode, triode. I don't know if you guys ever studied those. I did years ago. That's all we had. We never had transistors. The control grid is the element of the triode vacuum tube. The control grid is used to regulate the flow of electrons between cathode and plate. So I'm sure they'll ask that question in the test. The primary purpose of a screen grid in a vacuum tube is to reduce the grid to plate capacitance. That grid to plate capacitance can affect the signal being transmitted from the grid. The stable operating points for a bipolar transistor used as a switch in a logical circuit is its saturation and cutoff regions. Let's see what they're meaning here. Saturation is where the transistor is base biased for maximum emitter to collector current flow. Saturation is, okay, they got to have drawing here. Cutoff is where the transistor is base biased for minimum emitter to collector current flow. In a MOSFET, the gate is separated from the channel with a thin insulating layer. Okay, they're really throwing it out. An N-channel MOSFET, this would be the gate, this would be the source and the drain. So in a vacuum tube, you might consider this being the cathode, this being the grid, and this end up being where you take the actual current or the plate voltage. And indeed, this is how it would work. The load is placed here. This would be the load, which would be the plate of a vacuum tube. In effect, this is where the load occurs. And then here's the grid where you have a certain voltage applied to the grid, which then allows the current to flow between the grid and the D region here. And the voltage, the negative voltage is applied to this area here, which causes the whole thing to work, the electrons to flow. And this represents the return path. So it's like a vacuum tube, being that this provides the necessary current that's going to flow between here and here. And then this regulates the current. The approximate junction threshold voltage of a germanium diode is 0.3 volts. That's a simple diode. If you measure that with a voltmeter, you can see that. This is the voltage drop across the diode junction when it is conducting in the forward direction. So if I took my voltmeter and I was on one side or the other, I would see almost a dead short. But I reverse the voltmeter, plus on one side, minus on the other, and it's going to be an open circuit almost. The approximate junction threshold of a silicon diode is 0.7 volts. Okay, this is germanium. This is silicon. This is germanium, that's a silicon. Okay. This is the voltage drop across the diode junction when it is conducting in the forward region. Okay. A silicon diode will conduct current only if its anode is at a positive voltage compared to the cathode. It is then said to be forward biased. Okay. Silicon diode conduction current, forward bias. That's why it would be so reduced. The forward bias decreases the resistance of the diode, whereas the reverse bias increases the resistance of the diode. In forward biasing, the current is easily flowing through the circuit, whereas reverse bias, the circuit is cut off. An LED is forward biased when emitting light. So here's an LED, 3 volts here, and you see the direction of that. Look at that diode's symbol. That represents the arrow of the direction of flow. This a line across it, in effect, represents if you push something through here, it won't go because it's blocking. So that line is a blocking signal. So think of it that way, as if the signal is positive, it's going here. If it's negative, it will come here. So right now, this transistor is going to bring this thing to ground or bring this low. Okay, so that voltage now will light the diode because we now have a completed circuit. If this is not conducting, then this becomes open, and there's nothing there for the plus 3 volts to conduct through. And of course, the light emitting diode is when light shines on the thing, it can conduct. So that basically you're looking at a diode and a light emitting diode, and they're saying when a light shines on this thing, it will conduct, it will be in the full conduction mode, and 3 volts will be supplied to the transistor. And that's I guess that's the circuitry they're talking about, where it will turn on. And I guess they're putting in here epoxy wire band. They're showing you how it's made, the semiconductor, reflective cavity, a plus anode and a minus cathode. Array of LEDs and resistors. LEDs and resistors. Resistor, pulse network, keyboard. LCDs do not emit light. Therefore, a liquid crystal display requires ambient or backlighting. Liquid crystal displays do not emit light. And you've seen that in some of the old telephones and things or whatnot, where the background actually does the light, shows up the letters A, B, C, and D. Here we go. A black on amber LCD can easily be seen under any lighting condition. A black on amber display. The term MMIC means monolithic microwave integrated circuits. Boy, that's a microwave MMIC device. I haven't messed around with these, but they work. They're a semiconductor device, and they have a ground input, an output, and a signal input. Analog is also the term that describes an integrated circuit operational amplifier. Analog is a term that describes integrated circuit operational amplifiers. Schematic symbol of an analog amplifier, plus and minus. And this is what one looks like, a small little integrated circuit. A shift register is a clocked array of circuits that passes data in steps along the array. So you get a pulse in, and this is the clock at a certain clock period. If this is, I don't know, positive or negative at that time, when the pulse is either positive or negative, you're going to get an output, you know, depending on what device that is. And that output will go to the next one. And this one latches up and stores, the latch is stored over here, and it's stored over there, and it's stored over there. So it shifts. The register, it shifts whatever came in here, it shifts that output. And you can see the output of each on Q1, Q2, Q3, and Q4. So a shift register passes data in the steps along the way. And there's well, I won't go into the details here, but there's ways you can lock it up. So a signal appears here. The next signal appears a clock cycle away from that. And then the next clock cycle comes in and you see an output here. And the last clock cycle appears and you see an output here. So the clock appears starting from here and gives an output number 1. And on the next clock cycle, you get output number 2. And on the next clock cycle, you get 3. And in the last clock cycle, I wish they'd show a picture of it. Low power consumption is an advantage of CMOS integrated circuits compared to TTL, transistor logic integrated circuit. So a CMOS is made with different material. CMOS is the most commonly used digital logic family of integrated circuits. The term ROM means read-only memory. ROM. ROM is characterized as a non-volatile, meaning the stored information is maintained even if power is removed. It's like the chip in your iPhone. It can be written into, and you can pull it out, and still it retains the data. ROM is characterized as non-volatile, meaning the stored information is maintained even if power is removed. For a 2-input AND gate, high only when both inputs are high. That's an AND gate. And here's a description of an AND gate, and that's the pattern that you get out of it. So if A is low and B is low, C is low. If A is low and B is a 1 or high, you still get a 0 out. And if A is a 1 and B is a low, you get a 0 out. But if A is a high or 1 and B is a 1, you get a 1 out. So that's an AND gate. That's what they call an AND gate. This and this will give you that, not this or this. For 2 input NOR gates, the output is low when either or both inputs are high. So that's a NOR function. That's that symbol for a NOR function. And again, if you look at the logic here, 2 lows give you a 1, a 1 and a low give you a low, 1 and a low give you a low, a 1 and a 1 give you a low. So only this will give you a 1 if 2 zeros, 2 zeros. That's the truth table for the NOR gate. A 3-bit binary counter contains 8 states. Each flip-flop requires 2 input pulses to generate 1 output pulse. In short, being a base 2, a 3-bit is 2 times 2 times 2, or 8. 3, 2 times 2 times 2. Okay, oscillators and components. What are we're getting into the test now. What are the basic components of virtually all sine wave oscillators? What are the basic components of virtually all sine wave oscillators? An amplifier and a divider, a frequency multiplier and mixer, a circulator and a filter operating in a feedback loop, a filter and an amplifier operating in a feedback loop. What do you guys think?
That would be delta.
Yeah.
Okay. That's right. Okay, what determines the frequency of an LC oscillator? Inductance capacitor oscillator. The number of stages of the counter, the number of stages in the divider, the inductance and capacitance in the tank circuit, the time delay of the lag circuit. What would you say?
Charlie.
Yeah, Charlie.
Yeah, L is inductance, C is capacitance. So this LC oscillator, it gives you the clues of what's in the what's going to be the answer. Inductance and capacitance, inductance and capacitance. And you're right. Which element of a triode vacuum tube is used to regulate the flow of electrons between cathode and plate? A control grid, a heater, a screen grid, and a trigger electrode. Your answer is?
A, alpha.
Alpha.
Okay, I hear a lot of agreement there, and that's correct. What is the primary purpose of a screen grid in a vacuum tube? To reduce grid to plate capacitance, to increase efficiency, to increase the high frequency response, to decrease plate resistance. And your answer is?
Alpha.
Yeah, alpha.
Everybody think alpha, huh? Out there?
Yes, yes, I do.
Okay, that's right. What are the stable operating points of a bipolar transistor that is used as a switch in a logic circuit? Its saturation and cutoff regions, its active regions between the cutoff and saturation regions, between its peak and valley current points, between its enhancement and deletion mode. Enhancement and deletion modes. What is the stable operating? It's saturated
alpha
regions. Yes, you're correct. All right. Which of the following describes the construction of a MOSFET? The gate is formed by a back bias junction. The gate is separated from the channel with a thin insulating layer. The source is separated from the drain by a thin insulating layer. The source is formed by depositing metal on silicon.
Bravo?
Yeah, that's what I'm leaning towards is Bravo.
Bravo, the gate is separated from the channel with a thin insulation layer. Okay, you're right. Okay, what is the approximate junction threshold voltage of a germanium dial? 0.1, 0.3, 0.7, and 1 volt.
Bravo.
Yeah, Bravo, 0.3.
Everybody agree?
Yep.
Yes, sir.
Okay. What is the approximate junction threshold voltage of a conventional silicon diode?
Charlie.
Yeah, C, Charlie, 0.7.
Guys got good memories. That's good. How is an LED biased when emitting light? Beyond cutoff, at Zener voltage, reverse biased, or forward biased?
D, delta, forward biased.
Yep. Everybody agree? Anyone else out there?
Yeah, I'm on board.
Right. You got to forward bias these things. Which of the following is a characteristic of a liquid crystal display? It utilizes ambient light or backlighting. It offers a wide dynamic range. It consumes relatively high power. It has a relatively short lifetime.
A, alpha. It
Alpha.
utilizes
Guys, remember that. You see that in your mind. Yeah. What is meant by the term MMIC? Multi-megabyte lit integrated circuit, monolithic microwave integrated circuit, military specification manufactured integrated circuit, or mode modulated integrated circuit?
B, Bravo.
Yeah. Monolithic microwave integrated, very tiny device, isn't it? Remember the size of that thing? Okay. Which kind of device is an integrated circuit operational amplifier? Integrated circuit operate a digital, an MMIC, a programmable logic, or analog? Integrated circuit operational amplifier.
Yeah, D, delta, analog.
Remember that drawing? It had a triangle and had a plus and a minus and an output.
It seems
that's what it was. Okay, what is a shift register? A clocked array of circuits that passes data in steps along the array. An array of operational amplifiers used for tri-state arithmetic operations. A digital mixer, an analog mixer.
Alpha.
Yeah, alpha.
Hey, somebody out there said alpha, okay? That's right. Which of the following is an advantage of CMOS integrated circuits compared to TTL integrated circuits? Low power consumption, high power handling, better suited for RF amplifiers, or better suited for power supply?
Alpha.
I hear somebody say what? Say that again?
I think he said alpha.
Yes, alpha.
And does everybody agree?
It is alpha.
That's correct. Remember, CMOS has very low power. It consumes, and most things are built with CMOS right now. Well, there are transistors if you want higher power, but CMOS. What is meant by the term ROM? Resistor operated memory, read-only memory, random operational memory, or resistance overload memory?
Bravo, read only.
Everybody agrees with Bravo. Everybody. Yes, indeed. What is meant when memory is characterized as non-volatile? It is resistant to radiation damage. It is resistant to high temperatures. The stored information is maintained even if power is removed. The stored information cannot be changed once written.
C.
Charlie.
That is correct. Which of the following describes the function of a two-input AND gate? Two-input AND gate. Output is high when either or both inputs are low. Output is high only when both inputs are high. Output is low when either both inputs are high. And output is low only when both inputs are high.
Bravo.
Yeah, Bravo.
Output is high only when both inputs are high. And that's an AND gate. And that would be correct because you get all ones in, all ones out. Okay, which of the following describes the function of an input NOR gate? Output is high when either or both inputs are low. Output is high only when both inputs are high. Output is low when either or both inputs are high. And output is low only when both inputs are high.
Alpha.
output is high when either of both inputs are low. What do you think?
I think it's, yeah, C is what it is.
Oh yeah, that's
Output
right.
is low when either or both inputs are high. Okay. How many states does a 3-bit binary counter have? 3, 6, 8, or 16?
C, Charlie.
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 3 times 3 times 3. Okay. And that concludes that test. And we can move to the last one. I think we have one more. You guys still open for one more?
I'm fine.
When is lunch going to be?
You can have lunch anytime. I can have this. I can do this last test. Wait, let's see. I got 1, 2, 3. I did the third one now. Oh my gosh! Don't tell me. There are 2 more left.
Tom, comment.
Yeah.
Tom, this is Tim, K5TGS. I actually have 14. 14 is in section 4.
Oh, good. Okay, that's the last one. It is? Okay, wait a minute. Yeah, you're right. I got 10, 11, 12, 13. Yeah, there should be only 4 that I'm teaching.
Correct.
Right?
And then I'll pick up once they have their lunch.
Okay, I'm going to take off then 14, which is, yeah, I'll take off this one here, 14.
And 14's a long one.
Okay, now I'm down to 1. I'm going to be on chapter 13. So that'll be this one here when we get moving. Do I still have my screen shared?
No, sir.
No, sir.
Yeah. Okay. Well, listen, you want to take a lunch break and do this last one, or you want to bang through it now?
Just
I'm open either way.
Just be careful of time because I have 5 chapters to cover.
Okay. What I was supposed to end at noon? Something like that. Well, I don't know how many are in this next one here, but let me share my screen and then we'll get to the that. Let's see. I don't need that one. And what did I do? Did I mess it up again? Let's see. Hold on a second here. Screen sharing is stopped as it's closed. Okay. Okay. So now I got to go to screen sharing again. Come on, Tom. Share your screen. Oh. No. I'll tell you what I'll do before I share the screen. I'll pull up that one so I can see what it is. Otherwise, I have a hard time seeing what I got on my screen here. I got so much going on. Okay. 13. All right, now. There. Now I can play with this and share my screen. There, now I got it. So now we can see what this is. Otherwise, I didn't know where I was. All right, well, let's just cram through it. I don't know. Let's see how long it is here. Let me get an idea.
Yeah, you've got 50 slides.
50 slides, holy cow, that's a lot. Well, I don't know. I don't know if I can I make it by 1 o'clock? Is that going to affect you, Tim?
Well, yes, because I have 5 and at least the first one is quite technical and long.
Yeah.
Wow. Yeah, you'll just have to do the best you can.
Let me just ram through it so that at least we have the questions out there. I will do less of the. Let me just slideshow. Now I'll go through it, and Okay, so that's electrical. You're going to cover circuits, I guess, and the rest of them. Okay. 10, 11, 12, 13. Okay, electrical principles. I'm going to go through this. This is very complex as well, guys. So I will, to get through it quick enough so you can carry on with the rest of it, it's going to take be less comments here. 245 volts will be the voltage across 50 ohm dummy load dissipating 1200 watts. And then you use this formula, power. Okay. CE on the chart. There it is. Power. And it shows you the formula. Power type, resistance. And there's another formula there. And it's showing you the example. Okay, 244 volts. Those are things you guys are going to have to remember. That there's no other way to remember how to do it, especially when they give you that. Okay, CP on the chart. E equals R. Okay. Power equals E squared over R. Okay, that's giving you an example. Okay, 2.4 watts electrical power is used by a 12 volt DC light bulb, draws 0.2 amperes. Okay, and this has got to be self-study. Okay. So in other words, they're showing you the P in the chart. I'll just make one comment. And this area here is where power is. And that's what we're doing. See P on the chart. And it shows again, it's showing you that formula, I squared R. Okay. And then the next one, root mean square RMS. Measure of an AC signal, also called the effective value of an AC voltage. RMS is an AC type signal, measurement of an AC signal. So there's a peak voltage, zero voltage, peak voltage, and a relative amplitude of that voltage. Okay, showing that peak to peak voltage. If you combine two or more sine wave voltages, the RMS voltage would be the square root of the average of the sum of the squares of each voltage. You can't do anything with this except for memorize it, unless you know the formula yourself. Okay. Electrical principles. 12 volts is the RMS voltage. Boy, it goes right into peak voltage, RMS. Okay. It's just showing you that. RMS voltage is 12 volts. 12 volts is the RMS voltage of a sine wave with a value of 17 volts peak. RMS peak is 0.707, 17.707, 12 volts. 17 times 707. One advantage of a switched mode power supply as compared to a linear power supply is the high efficiency, a high frequency operation allows the use of smaller components. Switched power supply compared to a linear power supply. This is a regulated power supply showing the outputs. And this would be a regulated power supply, interior view of a switch mode power supply. And it's showing the bridge rectifier, input filter, transformer, output filters, things that you just have to look at. And they're very light. Electrical principles. 180 degrees is the portion of the AC cycle that is converted to DC by a halfway rectifier. Okay, here's a waveform coming in. This diode converts the AC into a half wave, cuts off the peaks. The diode only conducts in one direction. So only one diode is required in a half wave rectifier. Okay, half wave means it cuts off only in one direction, half of it. See? Okay, that's because you got one diode. 360 degrees is a portion of the AC cycle is converted to DC by a full wave rectifier. Now we'll get into full wave, and it will reuse two diodes. And this is the way it would operate. So now you get both of the waveforms. Okay. In full wave rectified power supply. There's the output power. And a series of DC pulses at twice the frequency of the AC input is the output waveform of an unfiltered full wave rectifier. And they're going to ask you that, I'm sure. Here's the input up plus and minus, and it ends up showing you the minus is right in between. So it just makes them twice, makes the plus side twice as fast, twice the frequency. Output of rectifier connects to a filter made up of the capacitors and inductors. Capacitors and inductors are used in a power supply filter network. Capacitors. There's a filter, leading resistor, capacitor, inductor. High capacitance for a given volume of it is an advantage of an electrolytic capacity. High capacitance for a given volume is the electrolytic capacitor. And these are big. These electrolytics are big. These high capacitors, they have a much higher capacitance than a tiny guy does. Most electrolytic are polarized, meaning they care deeply about which way you wire them up. Polarity of applied voltage is very important to polarized capacitors. Incorrect polarity can cause a capacitor to short circuit. And these high capacitance units, the big guys, they got a plus and a minus on them. You can't miss it. Reverse voltages can destroy the dielectric layer of the electrolytic capacitor. So if you reverse the voltage, you can destroy the electrolytic layer. Electrolytic layer. The capacitor should overheat and explode. All of these choices are correct. Okay, there's your big capacitor, and then on down. These are all electrolytics, but lower voltage. A useful feature of a bleeder resistor in a power supply is that it ensures that the filter capacitors are discharged when the power is removed. And this is a bleeder resistor. So if you were to remove the power from the power supply and you did not bleed off those capacitors, you could get shocked by the voltage. An advantage of a digital voltmeter as compared to an analog voltmeter is that it has better precision for most uses. Okay, digital and analog. When adjusting tuned circuits, the use of an instrument with analog readout may be preferred over an instrument with a numerical digital readout. When adjusting tuned circuits, the use of an instrument with analog readout, that's because it's variable in a way you can see it, okay, is better than digital. Sometimes that's true. High input impedance is desirable for voltage because it decreases the loading of the circuit being measured. Very high input impedance. A lot of good digital meters like I have are very high impedance. The analog needle movement can give the feel visually of tuned circuits, as long as that particular tuned circuit does not call for specialized non-loading measurements. An advantage of the low internal resistance of the nickel-cadmium batteries is that they can supply large quantities of current very quickly. Nickel-cadmium, large quantities of current, that's true. Always check the voltage of the batteries. The minimum allowable discharge voltage for a maximum life of a standard 12-volt lead-acid battery is 10.5 volts. Each cell should not be discharged below 1.75 volts. That's a lead acid. The process by which sunlight is changed directly into electricity is called photovoltaic. There's solar cells, solar panels, solar and wind power, all brought in here to a circuit and batteries. The approximate open circuit voltage from a modern well-illuminated photovoltaic cell is 0.5 volts. Open circuit voltage. The reason a series diode is connected between a solar panel and a storage battery is that being charged by the panel is the diode prevents itself self-discharge of the battery through the panel during times of low or no illumination. I hope you get that. I deal with this a lot. So you want to prevent the solar panel from discharging the battery when there is no when there's no sunlight. You put a series diode in series with the battery and the output of the solar panel. One disadvantage of using wind as a primary source of power for an emergency station is that a large energy storage system is needed to supply power when the wind is not blowing. There's wind power. And there's another wind power, small wind generator to keep a charge on a portable system. A direct fuse power connection to the battery using heavy gauge wire would be best for a 100-watt HF mobile installation. Okay, an HF watt mobile installation goes to the thing. I have larger battery, larger cables for my setup here. It is best not to draw the DC power for a 100-watt HF transceiver from an automobile's auxiliary power socket because the socket's wiring may be inadequate for current being drawn by a transceiver. Yeah, don't use a power socket. Go directly to the battery. Don't use that. Electrical principles. Okay. What would be, this is the question sound, what would be the RMS voltage across a 50 ohm dummy load dissipating 1200 watts? 173 volts, 245, 346 volts, or 692 volts?
B.
Bravo.
Yeah,
Bravo.
B.
1250 ohm, 1200 volts. Okay. RMS. Okay, that's correct. How many watts of electrical power are used if 400 volt DC is supplied to an 800 ohm load? P equals Z times I, or I squared R? What would you say?
Bravo.
Bravo.
Yeah, bravo.
200 watts, right? How many watts of electrical power are used by a 12 volt DC light bulb that draws 0.2 amperes? So you know.
Alpha.
Alpha.
You know, yeah.
Alpha.
0.2 times 12, huh? And it's alpha. How many watts are being dissipated when a current of 7 milliamperes flows through a 1250 ohm resistor? So you know resistance and that alpha. It's what is it? Current divided, ohms divided by current, right? Alpha. Okay. That's why these things are, to know that pie chart. Which value of an AC signal results in the same power dissipation as a DC voltage of the same value? The peak-to-peak value, the peak value, the RMS value, or the reciprocal of the RMS value?
Charlie.
Which
Charlie.
value? Exactly, we studied RMS. That's right. What is the RMS voltage of a sine wave with a value of 17 volts?
Bravo.
The sine wave, 12 volt.
Yep, bravo.
RMS. Okay. And how did you arrive at that?
Memory.
Just guess?
Memory.
Make sure you learn the formula, because they may not be the same. Which of the following is an advantage of a switched mode power supply as compared to a linear power supply? Faster switching time makes higher output voltage possible. Fewer circuit components are required. High frequency operation allows the use of smaller components, and all of these choices are correct.
Delta.
I agree with you.
Delta.
I agree. Oh no, we're both wrong.
No.
Frequency operation allows use of.
Oh, wow.
I thought of that first, but I thought all of the above. Faster switching makes higher power. Well, I don't know. I disagree with that. What portion of the AC cycle is converted to DC by a half wave? What portion? 90
Bravo.
degrees?
Bravo.
Okay.
Bravo.
Yes, you remember that half wave thing takes half of it, and it's half wave. What is the advantage of a half wave rectifier in a power supply? Only one diode is required. Ripple frequency is twice that of the full wave rectifier. More current than can be from a half wave rectifier, and the output voltage is 2 times the peak output voltage of a transformer. What do you guys say?
Alpha.
Everybody agree out there? I hear none. Alpha. What portion of the AC cycle is converted to DC by a full wave? 9 degrees, 180, 270, 360.
Delta.
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 Right? You remember that. 2 diodes in the circuit. Which type of rectifier uses 2 diodes and a center tap transformer? Full wave bridge, half wave, and synchronous.
Alpha.
Alpha.
Right.
Alpha.
Yeah. What is the output waveform of an unfiltered full wave rectifier connected to a resistive load? What is the output waveform of an unfiltered full wave rectifier? A series of DC pulses at twice the frequency of the AC input. A series of DC pulses at the same frequency as the AC input. A sine wave at half the frequency of the AC input. A steady DC voltage. Remember, this is unfiltered full wave rectifier.
Alpha?
Yeah, I think alpha.
I think you're correct. I would vote for alpha. Remember, without any capacitors to filter it, you just get twice the frequency. So it's a series of DC pulses at twice the frequency. What components are used in a power supply filter network? Okay, power supply filter: diodes, transformers and transistors, quartz crystals, capacitors, and inductors.
D.
Delta.
Delta.
Right. Which of the following is an advantage of an electrolytic capacitor? Tight tolerance, a non-polarized, high capacitance for a given volume, inexpensive RF capacitor.
Charlie.
Charlie.
Everybody agree out there?
Charlie.
Okay. That's correct. High capacitance. Why is the polarity of applied voltages important for polarized capacitors? Incorrect polarity can cause a capacitor to short circuit. Reverse voltages can destroy the dielectric layer of the electrolytic capacitor. The capacitor could overheat and explode. All the choices are correct. Indeed.
All are correct.
Yeah, all of them are
Delta.
correct.
Yeah, everybody knows that. Oh, incorrect. Well, now I think that's wrong. Incomplete can cause the capacitor to short circuit. That's correct. Reverse voltages can destroy that's correct. The capacitor could overheat and explode, and that's correct. They made a mistake here, guys, because all choices are correct. You want to go back and take a look? I can tell you from my own experience that that's correct. If you hook up a capacitor like that incorrectly, it can cause a capacitor to short out the dielectric. And the reverse voltage can destroy the dielectric for sure. Anyways.
Yeah, it is D. I looked it up.
Yeah, I whatever they did wrong on that. Well, maybe that was it. What safety features does a power supply bleeder resistor provide? It acts as, you know what, that last one seemed to come out wrong when I did my spacing. It's been working great, but it failed on that one for some reason. So let's see what happens here. What safety features does a power supply bleeder resistor provide? It acts as a fuse for excess voltage. It ensures the filter capacitors are discharged when power is removed. It removes shock hazards from the induction coil. It eliminates ground loop current.
Bravo.
Yes. That's bravo. See, now that worked. Okay. What is an advantage of a digital voltmeter as compared to an analog voltmeter? Better measuring computer circuits, better for RF measurements, better precision for most uses, faster response.
Charlie.
Charlie.
Yeah. What is an instance in which the use of an instrument with analog readout may be preferred over an instrument with a numerical digital readout when testing logic circuits, when high precision is desired, when measuring the frequency of an oscillator, when adjusting tuned circuits?
D, delta.
Delta.
All right, you guys are right. Why is high input impedance desirable for a voltmeter? It improves the frequency response. It decreases the battery consumption of the meter. It improves the resolution of the readings. It decreases the loading on circuits being measured.
D, delta.
D, delta.
D, delta is correct. Okay, what is the advantage of the low internal resistance of nickel cadmium batteries? Long life, high discharge current, high voltage, rapid discharge, rapid recharge.
Bravo.
Bravo.
That's right. What is the minimum allowable discharge voltage for maximum life of a standard 12-volt lead acid battery?
Charlie.
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 That's right. What is the name of the process by which sunlight is changed directly into electricity? Photovoltaic conversion, photon emission, photon synthesis, photo decomposition. What do you say?
Alpha.
Alpha.
Alpha. Okay, everybody says alpha. Correct. What is the approximate open circuit voltage from a modern, well-illuminated photovoltaic cell?
Bravo.
Open circuit.
Bravo.
Bravo.
Yes, everybody said bravo on that. What is the reason a series diode is connected between a solar panel and a storage battery that is being charged by the panel? The diode serves to regulate the charging voltage to prevent overcharge. The diode prevents self-discharge of the battery through the panel. During times of low or no illumination, the diode limits the current flowing from the panel to a safe value. The diode greatly increases the efficiency during times of high illumination.
Bravo.
Your answer is
Bravo.
Yeah, bravo.
yes, everybody remembers that one. Which of the following is a disadvantage of using wind as the primary source of power for an emergency station? The conversion efficiency from mechanical energy to electrical energy is less than 2%. The voltage and current rating of such a system are not compatible with amateur equipment. A large energy storage system is needed to supply power when the wind is not blowing. All of these choices are correct.
Charlie.
Charlie.
Yeah, I think so. You guys, everybody agree? All right, I'm with you. Which of the following direct fuse power connections would be the best for a 100-watt HF mobile installation? To the battery, using the heavy gauge wire. To the alternator or generator, using heavy gauge wire. To the battery, using resistor wire. To the alternator or generator, using resistor wire.
A, alpha.
Yes, alpha. Why is it best not to draw the DC power for a 100-watt HF transceiver from an automobile's auxiliary power socket? The socket is not wired with RF shield. The socket's wiring may be inadequate for the current being drawn. The DC polarity of the socket is reversed from the polarity. Drawing more than 50 watts from this socket could cause an engine to overheat. Your
Bravo.
answer is?
Bravo.
Bravo.
Yes. And that's the end of the session, or my session, I should say. All right, Tim, are you there?
I am here.
And I guess let's see. I'm not sharing anything now, and you have the con. From your point of view. But you know, I guess I'm sorry, nobody had lunch.
I've got a host disabled screen sharing.
Oh, you do? See.
Don't know why. He was supposed to set us all up to be able to share.
Yeah, I wonder did he give it to me to do that? Let's see.
Well, you had to have it if you were showing your power.
Yeah, he gave it to you, Tom.
Yeah, so let's see.
Tom's got to give it back.
Yeah, I see more breakout rooms, live to Facebook live. reaction recent. I'm trying to look for where
So
it
Tom,
said.
Tom, look at Tim's window, his video window, and at the top right corner, there's 3 little dots. Click
yeah,
on that. Click
see
on
it.
that and choose Make Host.
Make rename spotlight. Make host. Okay, there. Do you want to change the host to Tim? Yes, thank you. Yeah. Now that's you should give you the host, Tim. Thank you for that help.
All right. Am I sharing a PowerPoint now?
Not yet.
No, you're not.
Well, that's interesting. Let's see. I've got the PowerPoint up. I think I've got sharing on.
Share screen buttons at the bottom of the Zoom window.
Yeah, that's what I.
It might have not done it when if he just made you host it. You may have to click on it again.
All right, that may do it.
There you go.
Yeah.
Something's coming up now.
Okay.
Yeah.
All right, so you guys need to figure out your lunch break. We've got 5 different sections to go through, so it'll take time. And I obviously don't need to take a break.
Well, last week the session actually ended about an hour early. So if today's session had the same amount of information in it, then taking an hour lunch now and going until 5:30, which is the scheduled time, shouldn't really be that much of an issue. But I don't know how much time you're going to need for 5 sections. So.
Yeah, and I don't know. I didn't look at the sections last week. I don't know how many PowerPoint.
I can't remember.
Each one. But what do you guys think? You want to take a 30-minute break, come back at 1:15?
That sounds fair to me.
Anybody else?
Maybe 30 to 40, a little bit of leeway there, but yeah, a shorter lunch.
Okay, if we go to 1:15, that'll be about what? About 33 minutes.
Okay, that's good.
All right, well, I will be back at 1:15.
1:15.
We'll be ready to go.
Sounds good. Okay. Are you going to leave the Zoom session going?
Yes.
Okay. Okay, good. All right, let me mute that and mute that. And I'm going to go over here. Okay, guys, so here's what we're going to do. A little bit different format today. And, okay, a little bit different format today. No problem. We'll just kind of roll with it. I am going to end this session, take about 25 minutes. I'm going to go get something to eat myself. I'm just going to go inside. And then I'm going to start a new stream. So let's see. Yeah, I'll have to do that. In fact, I can go ahead and do that right now. So I can share the link with you guys in the chat. Let us go here. And I will schedule this. Schedule stream. That is fine there. Part 4. There, part 4. There, change thumbnail. I'll have to do up a new thumbnail later, but that's okay. I don't have any problems with that. So what we're going to do is going to take off 30 minutes. I'm going to end this stream, and I'm going to start a new stream so that there's a little break in there on watching the replays. And yes, I am going to chop it up and do a different section of it. But you know, it might take me a couple weeks to put that all together between because I'll have to do it in between all of my normal streaming and normal upload videos. So I will do that, but until that time, you'll have this stream to work on, or to watch rather. There's that. Okay, now get shareable link. Okay, I'm going to put this stream in the chat. That is where we will be starting in about, It'll start in about 30 minutes. He's going to start talking in 30 minutes, so I'll probably start the stream about 5 minutes early. And we will see you back there. 73, thanks for watching today. Do comment below if you have any questions or anything. See you back on the next live stream, and you guys have a good lunch real quick.